Alright, so I believe we're live. Hello, hello. Welcome, welcome. So here we go. Here's the actual working on the problem we were looking at yesterday. Here's my attempt at the solution. I've been kind of procrastinating, somewhat putting it off, but let's do it. Let's try our best. Do what we can. Do what we can do. And we'll sort of get right into it, I think, this time. I kind of was stalling a lot last time, and I started rambling about other things, but here we go. This time, try to solve it. So, as I said, the solution. So here's the question: wiggle sort 2, given an integer array nums, reorder it such that nums0, nums1, nums0 is less than nums1, which is then greater than the nums2, which is then less than nums3. So alternating numbers. So smaller number, larger number, smaller, larger, smaller, larger, etc. We assume the input array always has a valid answer. Example, nums 151164, 16, 15, 14, right? Small, large, small, large, and then 14, 15, 16 is also accepted, right? And 132231, 2, small, large, small, large, small, large, right? 2, 3, 1, 3, 1, 2, right? So that's what they're looking for, and they ask, can you do it in linear time, and or can you do this in place with constant extra space, which means not very much extra space, but basically. And the approach that I'm thinking to take is to do it in, you can use what's called quick select to get it in expected, almost certain linear time by picking random pivots. Use quick variant of random pivot quick select, and what you're going to look for is the n over 2 plus n modulo 2, that element. There's sort of the kth element, where k is, so if you were to sort the elements, there's sort of the 0th element is the first element, or the 1th element would be the second element, the index, really, the index of the elements, what you're looking for. What you want is, if you sort it, you actually want, it's basically the middle element, but actually potentially one more than that. It would be, you can actually do, well, you could do either one. So let's pick the n over 2th element. Let me just think. The problem is that if there's an odd number of elements, so let's say there's 3 elements, the smaller numbers can be the middle, the odd. So there's sort of, what you're looking for is basically you want to break the elements into 2 groups, larger numbers and smaller numbers. That's why you want to sort it, we don't have to sort it, but if you were to sort it, you would find sort of this median element, the middle element is what you're looking for. And if you have an odd number of, so if you have like 4, 4, 5, I would say you could look for 4. That's fine. The exact middle, the exact median is fine. But that would be 3 over 2 is 1, right? If you do integer arithmetic, which means you throw out your remainder. So 1 times 2 is 2, plus 1 gives you 3. So it would be 3 divided by 2 is 1, remainder 1, right? So if you pick 1, this is the 1th element, 0, 1. That would be, and then you add 1 to that. That would be the beginning of the larger elements, right? 4, 4, 5, index 2 is actually the larger elements. So that would be the n over 2 plus n mod 2, right? If it's odd, that you have an extra 1. If it's even, n over 2 at index, I think, is actually the larger numbers, right? So if it's 4, 4 divided by 2 is 0, 1, 2. It's actually the 3rd element. So yeah, so we can do, and if it's even, then obviously add. So yeah, okay, we can do it that way. That's fine. So n over 2 plus mod n over 2, that index, that's the element that we're looking for. We use quick select to find that. Now the reason why you do that is because that number is the smallest of the larger numbers, meaning you can effectively split into half of the elements. So half the elements are going to be larger, greater than or equal to, and the other half are going to be strictly less than. And why is that important? Is what we're going to do is then write a bijection to cycle and move all of the numbers in such a way where we can now have, I said there's a smaller, larger pattern that we want to do. So we're going to take this left side of all the smaller numbers and just kind of tie them in. So every other number is going to be a smaller number. And then on the right side, all these numbers are greater than or equal to that median number, and put those all in the second slots. And the reason why this is definitely should work is because all of the smaller numbers are less than this median number, less than or equal to, less than, it should be less than, not just less than or equal to, but strictly less than. And I think you can prove that they have to be less than, because if they're not, if they're less than or equal to, then you can actually prove that you won't be able to perform this sort that we're looking for. It won't be possible. And so because the smaller group are strictly less than and this larger group is greater than or equal to, that means that the smaller and lesser grouping that you do, you always have that the smaller number is going to be smaller than the median. It's always less than the median, and whatever number is in that second slot, the slot right before it, that's always greater than or equal to the median. So then that means the smaller number is always greater than any of these smaller numbers you pick is always less than any of these larger numbers you pick, and vice versa. Any larger number you pick is always larger than one of these smaller numbers you pick. So that's it. That's the solution. That's how we're going to do it. And let's see if we can. Let's see how it goes. I'm a little nervous because I haven't actually implemented quick select, but I believe we can do that, and probably can do it from memory. Like I'm stalling basically because I don't really want to implement it, but I should really be able to implement it, and I think I can. The way it's going to work is, the way quick select works is you pick a pivot, random pivot, and then you shift all the elements that are less than that pivot to the left side, and all the elements that are larger than that pivot to the right side of that pivot. And the pivot also gets moved to the correct position in the array where it's supposed to be, or ends up in the right position. Now, if that pivot is what you're looking for, if it has the index that you're looking for, you're done. You've selected the median, or you selected the index you're looking for. If not, then you've got to figure out, is what you're looking for to the right or to the left? Because you know the actual position, the actual median index that this would be if it was sorted, you can figure out. So if you're looking, so if your index is larger, that means you've got to recurse on the right side. If it's smaller, you've got to recurse on the left side. You pick a random pivot, and you do the same thing except only within that range. Again, and you move everything around again. And so you do that a bunch of times, either on the left side or the right side, and you recurse, and you basically keep shrinking the range of numbers that you're iterating through until, and finding out where the indices of these each sort of sorted values should be, until you get to your pivot. And then what we're going to do after that is then we're going to do the same, basically rearranging that we did, where we move all the smaller numbers to the left, all the larger numbers to the right. We're going to use that pivot and do that on the whole array. So we're going to run that routine one more time, and then we're going to run that bijection that we were talking about before. So there's a couple of pieces here. Is randomly selecting the pivot would be, we actually want a range on our quick select. It's going to be the range over these numbers, and we are going to modify this, by the way. This set of numbers, we're going to modify this, right? Because that's what they're looking for. We want it to be sorted when it's done. So what we would do is we want some randomness. Now, I don't do that too often. I don't mess around with that too much, and I'm thinking, how do we actually randomize things? Let's see. Oops. We don't want to use rand. This is not the best way to do this. There's a way that's better. Yeah, there's no quality control for the random numbers in rand. And the reason why you don't want to use this in general is because you don't necessarily know what systems you're going to be working on, and the implementations for rand can be kind of arbitrary, as far as I know. And they're saying that some implementations in the past have been pretty bad. And so the thing is that like sometimes people use randomness for like basically for like passwords or things like that, and you can pretty much, if you can predict the randomness of what is generating the thing that you're looking for, then you can possibly crack, like for instance, figure out someone's password, something like that. That's like vaguely why you don't want to in general use rand. So let's not do that. We're going to use instead a random number generator, which is a little bit different, and this is going to be from the numerics library. Where would we like? Oh, it's in random. Okay, yeah. I want the random header. So I actually forgot about that. You kind of would just assume that you can easily get random numbers, which you can, but in C++ it's like kind of involved. So you want, I think I usually use a Mesonate twister engine. I usually use one of those. I think I forget what I generally do, what I use, and I usually just follow the example. I think uniform distribution should be fine. I think also. Random device, yeah. Real random value if available. I think I usually use the system clock for the random device, right? I forget how this works. Uniformly distributed integer random number generator that produces non-deterministic random numbers. Device may be implemented in terms of implementation defined. Pseudo-random number engine if a non-deterministic source is not available to the implementation. In this case, each random device object may generate the same number sequence. Interesting. A notable implementation is deterministic in old versions of min-GW. Latest could be, yeah. Gotta be careful with this stuff. Random device RD. Hist. Uniform int distribution. Hist map dist RD. Performance of many implementations of random devices. Device degrades sharply once the entropy pool is exhausted. For practical use, random device is generally only used to seed a PRNG, such as pseudo-random number generators and Mesonate twister 19937. Implementations of this degrade sharply once the entropy pool is exhausted. Performance. How are you supposed to do this? You know, like I don't even know. I always get in this kind of like, whenever randomness comes up in questions, I always get like this like fog of like, wait a minute, how am I supposed to implement randomness? You know, what's the right way to do it? It's like I don't actually know. I'm not really sure. Yeah, because there's like all this stuff going on with like the quality of the randomness, basically. You know, you want to have good quality randomness, and so I always screw it up, like because I'm always just like, oh, I just want to use srand and call it a day, or rand and call it a day, but it's not good. Not good to do it that way. As with many things in life, the answer is usually quite a bit longer. In simple, you don't have a simple answer, right? It's just you gotta do your research to figure out what's a good answer. Yeah, pseudo-random number generation. It's funny too because it's like when you need it, you're like, wait, now I gotta do all this research to figure out like how do I do this? Yeah, that's kind of funny. It's good to like kind of look ahead in the future, so you can learn about things before. You know, you're sitting here thinking, wait a minute, how do I even generate these random numbers? Random number library provides classes that generate random and pseudo-random numbers. These classes include uniform random bit generators, URBGs, which include both random number engines, which are pseudo-random number generators that generate integer sequences with uniform distribution, and true random number generators if available. Random number distributions, uniform, normal, Poisson distributions, which convert the output of URBGs into various statistical distributions. URBGs and distributions are designed to be used together to produce random values. All of the random number engines may be specifically seeded, serialized, and deserialized for use with repeatable simulators. So what you do with a seed usually is you give it a number, and it uses that number to kind of like configure itself. It's usually a random number of some kind that comes from some like static noise. So like as an example, what's the current time? If you get that, you can give that the seed, and obviously every time you run it, it's a different time. And usually it's time measured in seconds, and the seconds are usually measured from like the beginning of a certain point. They call it the beginning of epoch, which I don't actually know what point in time that is, but it's like a long time ago, basically. So you always get this like big random number of seconds, and it's always a different number every time you call it. So your program is kind of uniquely seeded with randomness each time because it has this different number every time to work with. However, that being said, it's there's a few things about that. I guess the first thing is like you can kind of like, you got to be careful even with something like that, because you can kind of reverse engineer. If you happen to know that that's how the program is being seeded in terms of time, then actually you could just approximate, well, when was this executed, this function, and what pattern do you think they were using? You can reverse engineer, like when did they call this function, and what distribution did they use with this function, because they probably seeded it with the time, which now we know that they seeded with the time. So now we can figure out, we can actually recreate, we can reseed the same engine that they used with the time to then generate the sequence that they're using. And again, crack passwords that way if you really wanted to, right? So like I think there's what they call RSA engines. Like if you knew that a certain company was using an RSA token generator and it generates sequences of numbers, and you knew also the manufacturer of that product, of those sequences, you knew the manufacturer, you knew the people that worked for that manufacturer, and you knew the specific habits of those people that work for that manufacturer in terms of how they write their code, you can actually go so far as to figuring out basically RSA keys and break into you could break into certain systems, certain codes. You can actually figure out what the sequence is, guess the sequence. That's pretty wild. I haven't thought about that, but yeah, there's like a lot of stuff you can do in terms of security with regard to randomness, because randomness is used for a lot of encryption. A lot of different things use randomness somewhat. Excuse me, I think so. It's like, for instance, anyway. So, yeah, randomness is like a tricky thing. We're actually not doing any security applications here, but that's the problem, is that you want certain properties when you're dealing with randomness. And it kind of doesn't matter that much, I guess, if we're seeding things. I don't know. You have to figure out how secure do you want to be, and like what's the application, and like what are we doing exactly. There's such a thing as like cryptographically secure random number generators. So this is it's quite a name. It's CSPNG engine, or CSPNG. I'm sorry, pseudorandom. CSPRNG, yeah, C-Spring, C-Spring generator, or yeah, it's cryptographically secure pseudorandom number generator, right? So this is like another level of RSA, SSA. This is like another level of randomness, and right, exactly, RSA, PKCS. Number 1 is first family of standards called public key cryptography standards. RSA Labs. So provides basic definitions of and recommendations for implementing the RSA algorithm for public key cryptography. Defines the mathematical properties of public and private keys, primitive operations for encryption, signatures, secure cryptographic schemes, and related ASN. 1 syntax representations, current version. Yeah, it's like Hackerman's. Hackerman's breaking into things, you know. No, there's RSA is kind of interesting. I don't know too much about it really, but I just know that, as I was saying, like how you generate your certain random things. So salts, right? So salts are a basically like an extra additional piece to. I think it depends on what you're doing, but it basically it's random data, right? Additional random data that uses input to a function, right? Here we go. Cryptography. Salt is random data that is used as an additional input to a one-way function that hashes data, a password, a passphrase. Salts are used to safeguard passwords in storage. Historically, a password was stored in plain text on a system, but over time. So basically, this adds extra randomness, right? It's like so this random data, this extra randomness, the salt could be generated from, as you just saw, like some pseudo-random number generator, and you really want a cryptographically secured pseudo-random number generator when you're generating that salt, because as I said, if you're just from just a few pieces of information, like if you know the programmer and you know their habits and you know how they would typically code up their random number generators, you can maybe guess at how, like for instance, if they typically use time as a seed, if that's like a common practice. There are like probably all kinds of other common practices that you can create like a database of different practices that people do, and just run through all these different scenarios to try all these different possible cracking schemes, stuff like that. I mean, there's like all kinds of things you can do, but like that's just like something just I realize as we're talking, like you could do something like that if you wanted to. Yeah, that's kind of like a mixture of like social engineering and just clever try to crack into something, hack into something. Clever cracking. There's different. The reason between cracking and hacking and programming is like, you know, cracking into something is usually means it's like slang for basically trying to do something maliciously. You know, break through security. I guess I don't know. I'm not sure if that really matters. I don't know. I don't really. It's not like I think people who are trying to break into things really spend a lot of time talking to each other. I don't know. I have no idea. It's not a world I'm familiar with. Let's put it that way. I'll just say I'm not familiar. I wouldn't know if anyone even bothers to make the distinction between cracking into something or just programming something or breaking, hacking. But yes, nonces are also like I don't know. So key generation, I guess, kind of makes sense. You'd want to have this. This is also randomly generated. And it's the encryption decryption scheme. So again, like if you could guess what someone's key is in like private public encryption schemes, like again, if you could figure out like, okay, what software do you think they used to generate the key, and then like who made that software, and then like what are the habits of that programmer when he makes random numbers. what do you think is likely the sequence that they used? You could possibly predict the keys. And instead of trying to break the keys directly, which, by the way, is another thing, you can technically do that with quantum computers now. A lot of these keys can be broken backwards, or actually broken directly. That would be kind of a backwards going. Yeah, that would be kind of a reverse engineering approach to do it if you want to do it the way I was just describing. What are nonces? Nonces are similar to salts. It's another like random number. Cryptography, a nonce is an arbitrary number that can be used just once in a cryptographic communication. It is similar in spirit to a nonce word, hence the name. It is often a random or pseudo-random random number issued in an authentication protocol to ensure that old communications cannot be reused. The only time I've ever even like encountered nonces in terms of like programming stuff is when I was messing around with sending messages back and forth between servers. So like there was a period of time where I was trying to, I wanted to trade Bitcoin, and I wanted to trade it algorithmically, and I think I had to add nonces to the requests that I was making to the servers, something like that. There's another time that I was messing around with nonces. I think a friend of mine was showing me how he would implement something for some system I was working on, and yeah, it was. But yeah, I don't have too much experience with the nonces. But yeah, I remember I put like a few $1,000s in a Bitcoin. That was like years ago, and I was trading it, and I made a few bucks. I had some algorithm that I wrote, and it was kind of neat. But I needed more money, and I also needed not just more money. I needed more volume. That was the problem. I couldn't. It was illegal for me to trade on the exchanges in that I wanted to trade on, so I couldn't get the volume to trade enough. But I did make a few bucks, which is kind of cool, kind of neat. But yeah, and I even around that time I even traded. What is it? I got into a program for trading options and futures on Bitcoin, which basically, if I had taken advantage of that, or when I had the opportunity, I had like $2,000, like actually tens of thousands at the time. And if I had bought like options on Bitcoin at the time, I would have made like a few million, probably a few billion, possibly. Like we're talking like 1,000 multiple. No, I'm sorry, no, not a few billion. No, that's way too much. Well, no, I don't know, but yeah, like thousand, like there's multipliers that you have just from like big changes. But with options, it's basically like you could have an option that's worth like 10 cents becomes worth like $10,000, and that would be a huge multiplier if you did that. That's at 100,000 times. Yeah, so like 100,000 times 10 grand would be a lot. Is that a billion? I think so, right? 100,000 times 10. Yeah, that's a billion. Yeah, actually, I could have made $1 billion, probably. Yeah, because around that time, I think Bitcoin was trading at like, I don't know, like $8,000, something like that, and then it went up. It went up over to way over 10,000. I think it was some point it was trading at like 50 grand. I don't remember exactly the number, but it was pretty high. And yeah, actually, you could have had a 10,000 time. You could have had 10 cents to 10 grand options. Yeah, definitely. Wow, that's pretty wild. But anyway, yeah, basically could have been a billionaire if I wanted to. If I'd take advantage of that. That's pretty wild. Now here's the interesting thing is that who's to say you still can't, right? Who's to say I couldn't just go buy Bitcoin options, and it jumps up another, 50 grand or whatever, and there you go. Now you're a billionaire. Now you are a billionaire. Anyway, rambling now, but yeah, I mean, sure. So basically, I don't know very much about this stuff either. I'm not super interested in learning about it very much, quite frankly. All I want to do is get my random numbers correctly, right? That's all I'm looking for. I'm not looking for I'm not looking for anything crazy here, or anything more. I don't want to know that much. I really don't want to know that much, quite frankly. 2017. Huh. Don't use hard-coded keys. Nice. Yeah, hard-coded seed key. There you go. Yeah, here's exactly an example where they launched an attack. Attacker can brute force encrypted data to discover the rest of the encryption parameters and deduce the master encryption key used to encrypt web sessions or virtual private network sessions. There you go. During World War II, Japan used a cipher machine used for diplomatic communications. The United States was able to crack it and read its messages, mostly because the key values used were insufficiently random. That was the Japanese purple cipher machine. Yeah, that was also in World War II, where the radio, was it the radio waves they were sending messages on, the Germans? There was a fellow who actually cracked codes in World War II, and I want to say it was Simons. I keep bringing up Simons, Jim Simons, the billionaire. Over the years, I've brought him up quite a bit in my streams, but he I think he was a code cracker way back when. I want to say it was him. I don't recall, but that was the thing, is that you could decipher the encryption for messages sent over radio. I want to say it was radio waves. I want to say that's what it was, and I'm not actually sure. And you can use basically just maths to figure that out. Try to figure out what the scheme is that they're using. And I guess basically back then the things were so rudimentary that it was possible to break stuff, to crack into things. But as you see here, right, with Japan, but I don't know. Well, that actually might be what I'm thinking of, by the way. Actually, that might just be it. It's like literally the Japanese communications, Japanese cipher machines. Ciphers are generally not that hard to break, by the way. Ciphers are in particular are like, yeah, they're like one of the easier things to break, as far as I know. I don't know too much about it, but like I can kind of imagine, because ciphers themselves, I think typically are like literally. Usually when the most of the times when I've heard it in context, ciphers, they're referring to like just a mapping of characters, just a bijection, which is like really simple. Like it's actually like a really easy, like you could probably figure that out by hand, which letters are mapping to what, and you just kind of keep trying different combinations until kind of process elimination until you have like at least just like one word that makes sense, and then say, okay, this is probably this part of the cipher, and then you can kind of keep moving characters around until it seems like it's a legible message, and then once you've moved enough, then you can actually just get the whole cipher, and then once you have your cipher, if they keep reusing it, then you can read all their messages. It's not encrypted anymore. Yeah. Huh. So, what are we doing here? I want random numbers. I don't think it needs to be super. It doesn't need to be secure. It's not I'm not doing any cryptography here. We could probably just get away with like a random device, however that's implemented, and then use a uniform int distribution. I guess we'll use that. That could be fine, I think. What is this? Do we want ints? Yeah, we do want ints, right? We do want int distribution. What are the other distributions defined in the header here? We have a uniform random bit generator. I think this uniform int distribution is let's look at the random library. I see a uniform random bit generator. What's a concept? Okay, got it. Classes. So C++ 20 concepts. Yeah, I heard C++ 20 was going to have concepts. I remember that was years ago. I was talking with my coworker about that. He was like, "Yeah, man, C++ 20 concepts are coming out in C++ 20," and I was like, "That's gonna be a long time before we start using those." Oh, here they are. They're here. What the heck is it? At the time, I was like, I don't really know or care about what those things are, and I don't want to go learn them. But now I guess it's part of C++ standard, which is like, huh. I still don't know what those are. Still don't understand what those are. I don't know. I need to learn concepts now if I want to call myself a C++ programmer. I don't know about that. Model only if given any object G of type G, G is in this range, G is amortized constant complexity, semantic requirements. Interesting. Random bit generator. I guess I'll have to learn about concepts. Concept, uniform random bit generator, invocable, G, reference, which I'm not sure what that means. This is a R value reference, standard unsigned integral, invoke result, T, G reference. I actually don't know what these, I think it's and, maybe this is not an R value, but this is actually a, I don't know anything about concepts. I don't know what these things are. I don't know, not one thing. I guess these are, I think it's actually a logical and then requires a bunch of things. Gmin, Gmax, same as invoke result, same as invoke result. Requires bool constant, Gmin, Gmax value. I have no idea what's going on here. Not a clue. Not a clue. Not gonna use concepts as long as I can. I can avoid it. I don't want to learn more about that, man. No thanks. No thank you. Random number engines. Okay, linear congruential engine, Masonry twister engine, subtract with carry engine, discard block engine, independent bits engine, shuffle order engine, predefined generators. Okay, Knuth B, shuffle order engine, default random engine. Interesting. I think the random device, non-deterministic random numbers. Okay, non-deterministic random generators, hardware entry source. Okay, I see. So I think your hardware will just provide you some random thing. I don't know. That's interesting. But okay, so these are deterministic random generators, I guess. A number engine adapter. A number engine. Yeah, see, this is like a lot to just like generate random numbers, you know? Like, you just need some random numbers. You just get this whole library of stuff, and you're like, where do I even begin? What do I even do with this? Uniform int distribution. Okay, there you go. So there's one, and then uniform real distribution. Like that's usually what you need. Just integers and real numbers, and do it uniformly. It's probably enough. But you do have Bernoulli distributions, which are like true and false values. Binomial distributions, which give you integers. A binomial distribution, which is a little bit different from uniform. A negative binomial distribution gives you. I actually don't know what a negative binomial distribution is. And then geometric distribution is also slightly different. Poisson distribution is different as well. Exponential distribution, gamma distribution, Weibull distribution, extreme value distribution. These are all different kinds of probability distributions. Probably for real numbers, I guess. Normal distribution, log normal, chi squared, Cauchy, Fisher, Fisher F, student T. Student T is something you'll study in the stats class at university. That comes up. Discrete distributions. This is integers. Yeah. Piecewise constant. Oh, that's interesting. Constant subintervals. Piecewise linear. Real values. These are both real. Oh, interesting. Seed sequence. General purpose bias limiting scrambled seed sequence generator. Like, doesn't this feel like you're in like watching like a sci-fi movie or something? Like, general purpose bias eliminating scrambled seed sequence generator. Say that 10 times fast. How many words are there? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 different words to describe this thing. That's the name. It's like that's name, but like the basic description is 8 words. Seed sequence. Also, note, and I appreciate this, if people give me a hard time about using a snake case, it's called, where you have the underscore, you see these classes? These, since C++ 11, these use snake case to define their classes. Aha. So if anybody bothers me, I'm going to point them to this page and say, hey, give me a hard time by using snake case, okay? See this? Generate canonical. Evenly distributed real values of given precision across 0 to 1 functions. Okay. Wow. Whew. Ooh-wee. Oh boy. Excuse me. So we have concepts. Like, what is a concept in C++? We're going to have to go look that up now. I said I was going to write the code for this problem, but I just got distracted. I got distracted. Okay. Negative binomial before a specified number of failures occurs. For example, we can. It's like, what is the difference between the negative and the regular binomial distribution? What are those things? Where is it? Yeah, there's the binomial and negative binomial, right? You ready? So, I don't know, I wanted to see the, you're not going to take me to the, that's going to take me to the, the Wikipedia page for the binomial distribution. Also, this is interesting. You have random device, GenRD, generator, D, form 4 trials. So, oh, you use a generator. Oh, interesting. Okay, maybe I should use this. MT, yeah, okay. No. Of the number of successes in a sequence of n independent experiments asking a yes/no question, and each with its own Boolean valued outcome. Number of successes in a sequence of independent identically distributed Bernoulli trials before a specified. By the way, it's like the same thing. Bernoulli trial is just a yes or no question. Before a specified non-random number of failures occurs. Oh, interesting. Okay. For example, we can define rolling a 6 on a die as a failure and rolling any other number as a success. How many successful rolls will occur before we see the third failure? In such a case, the probability distribution of the number of non-sixes that appear will be a negative binomial distribution. We can similarly use the negative binomial distribution to model the number of days a certain machine works before it breaks down. Okay. And the Pascal distribution and the Polya distribution are special cases for the negative binomial distribution. Interesting. Negative binomial. Probability mass function. I'm looking for alternative formulations. Excuse me. Wow, there's a lot going on here. There's a lot going on here. This is the binomial distribution. R successes given in trials. Okay. So this is like somewhat related to the binomial distribution. But it's slightly different. I forgot what this even means, probability. I took statistics in university. How many years ago was that? That was something like 8 years ago. That was actually my first degree, or not first degree, I double majored, so that was the first major that I took. Yeah, double majored in applied maths and computer science, and applied maths was applied maths and statistics. I usually don't say applied maths and statistics and computer science because it confuses people. The applied maths and statistics is one degree, one major, and then computer science is another major. But I majored in both of those. And yeah. Probability of the discrete random variable is exactly equal to some value. Okay, discrete density function. Probability mass function is often the primary means of defining discrete probability distribution. Hence, such functions exist for either scalar or multivariate random variables whose domain is discrete. A probability mass function differs from a probability density function in that the latter is associated with continuous rather than discrete random variables. Yeah, probability mass functions and probability distribution functions are interesting. So probability density function basically gives you the probability it's usually like it's continuous, right? Yeah, the density is continuous, which I don't know, mass and density is kind of probably arbitrary with the words that they used to define these things, but the latter is, it's continuous rather than discrete random variables. Continuous random variables, it's weird because like basically that means they could be any real value rather than if it's continuous rather than any discrete values, which is significant and different. Yeah. PDF must be integrated over an interval to yield the probability. Yeah, I was gonna say, I think, I think you actually, right, you take the area under the curve on a PDF to actually give you the actual probability, and it's a probability that you're between certain values, something like that. I don't actually remember what like the interpretation of a PDF is with regard to how its relationship to probability. Value of the random variable having the largest probability mass is called the mode. Interesting. So a uniform distribution, by the way, is a probability mass function where every integer, uniform int distribution is every integer has the equal probability of occurring. So yeah. And then actually they even ask you to one question that you'll be asked, or possibly potentially, is how do you can you design an algorithm that generates a uniform int distribution, right? Which is challenging. How would you do it in practice, and then how would you could you come up with an algorithm that does that? Which for me is actually rather difficult. I think the short answer is to do what we're doing right now, which is basically use the C++, use the C++ built-in. But if you didn't have the C++ library to lean back on, what would you do, right? It's probably an implementation you could find. Yeah, it's an interesting question. I gotta like refresh my memory on that question because I would get that wrong. I get that wrong every time because I always forget. I always forget. There's I forget. Just say I forget. There's like ideas that I have for that answer, but I don't. I shouldn't just say I forget, but I think I never actually got that like nailed down the answer to that question, what it should be. So this is how you do it. You get a random device, use a Mesonnet twister, and generator, and then you use your generator. That's what we're gonna do. Just do that. We also want to learn about concepts, right? I have to put that on my list of like things to eventually do. Is go learn about what algorithm would you use for your uniformly distributed integers if you didn't have, you know, a random device and a mesonet twister and the C++ STL to just quickly whip up an distribution, uniform distribution. Create account, it says. Oh, no. Okay. Oh, you can create an account. I'd like to do that. Concepts. Oh, that's interesting. Concepts library. Oh, this is a whole shindig, isn't it? Oh boy. Oh boy. I wonder if the G++ compilers support this yet. I hope they do. I mean, it's already 2021, right? So in theory they would. Wow, man, it's pretty wild, like how quickly things go. Definitions of fundamental library concepts that can be used to perform compile time validation of template arguments and perform function dispatch based on properties of types. These concepts provide a foundation for equational reasoning in programs. Most concepts in the standard library impose both syntactic and semantic requirements. It is said that a standard concept is satisfied if its syntactic requirements are met and is modeled if it is satisfied, and its semantic requirements, if any, are also met. In general, the syntactic requirements can be checked by the compiler if the validity or meaning of a program depends on whether a sequence of template arguments models a concept and the concept is satisfied but not modeled, or if a semantic requirement is not met at the point of use, the program is ill-formed, no diagnostic required. Concepts header, define the standard namespace. The concepts library defines definitions of fundamental library concepts that can be used to perform compile time validation of template arguments and perform function dispatch based on properties of types. Whoa! Function dispatch is a significant thing. I think this has to do with what do they call that? What's it called? Overloading. Overloading. I want to say it's overloading. Yeah. When you have different names being used in different contexts, and you want to figure out what is it supposed to mean in that context. That's the function dispatch. I think it basically optimizes your programs to, instead of doing runtime function dispatching, you can do compile time function dispatching, and then basically your compiler can figure it out during compilation rather than when you're actually running the program, thereby optimizing the program. I want to say that's I want to say that's what's going on there, but I'm actually not sure. I don't really know too much about function dispatch. Concepts provide a foundation for equational reasoning in programs. I don't really know what that means, what equational reasoning is. But pretty interesting. Same as derived from, convertible to, common reference with, common with, integral, signed integral, integral type, signed integral type, unsigned integral, floating point, assignable from. I want to say maybe this is referring to like, yeah, like I don't know, I guess your inputs need to be like certain types, maybe like an integral type, or input has to be a signed integral, something like that. Input has to be a floating point, things of that nature. I don't really know. These aren't just inputs though. I think these are templates, inputs to templates, so classes that you use within a template. Yeah, because templates, it's kind of like the Wild West with templates. Like you can use any kind of class you want as an input to your template, and then maybe you want that input, you want to basically assign restrictions to those possible inputs for templates. I think I get it now. I think I understand what they're going for with this. Okay, that makes sense. Yeah, it's pretty interesting. Swappable, destructible, constructible from, default initializable, move constructible, copy constructible. Yeah, because templates are kind of, like I said, kind of wild. Like you really can get into some like really funky situations with your templates if you just put like all kinds of random classes as the inputs for the templates. Like you can get into situations where things just don't make sense. I actually really don't do. And there's templates, and there's template programming, and there's template meta programming, which is like, this is kind of like, I guess this would be like template. This would be like meta programming. Meta programming of your meta programming would be like defining a concepts library. The meta. Increase the meta. Yeah, it's... Huh. Okay. Okay. So anyway, right. We just need random numbers, you know? We just need some random numbers. Yeah. All right. Let's start with that. Let's start with just getting some random numbers. So we have random device, RD. We have a Mesonnet twister, which has a whole it's an engine. There's a predefined this one 19937. For some reason 19937, like I'm not gonna remember this. I have to look that up every time. I have to look that up every time. It's also interesting, this is from 10 years ago. Like 2011 was 10 years ago. Like I remember looking at yeah, I remember looking at my C++ book 10 years ago, roughly, a long time ago, and looking at like, oh yeah, C++ 11, like, oh, they're gonna have all these new things in C++. Here I am 11 years later, and I'm like, oh yeah, they have all these things in C++. I still don't understand. Oh, it's so funny. I'm still like, oh yeah, 19937. Yeah, I have to like memorize that. Oh boy. And look at all this Mesonnet twister. You can kind of, yeah, like, see, that's the thing. It's like you could it's also from 1998. These twisters. You can basically, if you know the programmer is like the kind of person that would just plug and play with his Mesonnet twister straight from this, you know, C++ standard, you can actually guess like the random generator. Like you could be like, oh, it was probably just the random device on the hardware, and then also the Mesonnet twister, and then you can probably guess a lot of stuff. I do wonder if you can guess. The problem, I guess, is that it's non-deterministic. You'd have to guess like the hardware, what the hardware device, how it generates its random numbers, the sequences. But even the hardware device, like the random number generating for that hardware, probably you can get a copy of that hardware and then probably generate random numbers, figure out how they're generated from there too. But by the way, it says non-deterministic, but it's like that may not be the case, right? That may actually not be true. Hardware's probably has something that, not maybe, I don't know how deterministic it would be really, but I don't know, just thoughts. Never tried it or done any of this, but it sounds like it in theory it's plausible. And now you have uniform int distribution, D of this generator. Oh, or no, what is this? let's look at the constructor. That's what I'm looking for. A, B. Do you give it a distribution? Parameter set. Does it really need a parameter set? What would the parameter set be? Param type, params. A is the distribution parameters. Params is the distribution parameters. I guess I don't know what this would be. New contents of the parameter set. Yeah, but like what? Param type. Is that like a pair? Like I don't know. I don't see an example of. Oh, I see. You seed it with RD. You call RD to get the seed of the. Excuse me. Yeah. So you create this with this seed, and you take the seed from the random device, and then you use this generator as the engine for the distribution. Next random number. Reset. The type of the parameter set C random number distribution. Yeah, what is that param type? Function object returning random numbers according to a probability density function or discrete probability distribution. D satisfies random number distribution if D satisfies copy constructible, copy assignable given T, the type named by result type, P, the type named by D param type, which satisfies notes, expression. I don't really get it. I don't know. Like, I just want to know if I want to change the parameters. Like, is that a pair of numbers? Is that a vector of numbers? Like, what do I set if I want to set the parameters? Like, what do I use? What do I do? It's really simple. A really simple question that I have here. Also, forgive me for having the buzzing this whole time. Yeah, I took that out. Should be charged up now. I don't need to have the buzzing. What I don't know. I don't see very much about the parameter type. Whatever, that's okay. It's fine. Don't really need to know that. To do what I need to do here. However, this is interesting. This takes the generator sometimes. It always takes the generator. And you can take parameters. Oh. Interesting. So you can associate a parameter set, and then you can use a parameter set. Like, I want to know, like, what if I call this with, what if I call this with, I don't know, like a pair of numbers or something. It's so weird to me. Like a vector of numbers. What would that do? Would it work? Find out now. All right, we'll associate it with 0 to nums.size minus 1. Right, so we're getting a random index. Right, these are going to be the indices. And actually, you can just give it new parameters each time, right? So let's try D of generator. Let's do it like a bunch of times. 1, 1, 1, 2, 3, 4, 5. Let's take these test cases. Hold on to these. Let's just take the second one for now. Let's do the first one for now. Okay. Got this first one. And it says okay, 03041. All right. Interesting. Now, how many numbers do we have? 0, 1, 2, 3, 4, 5. Okay. Now, 0, 1, 2, yeah, 6 numbers. Okay. We want gen 0, 100. Do that 3 times. What does that do? Okay. Use an initializer list. Does that work? First, I want to get it to compile, right? Okay. Param type. It's a const param type. I don't know what that is, you know? Can we auto p equals 0, 100? Does that work? What does that do? Okay. What about, all right, ready? Const standard uniform int distribution int param type. We'll call that p. And now, okay, what does that do? Oh, it compiles. Okay, but what? Okay, p of 0 to 100. No kidding. That works. But what is this? What do you mean? What is this? Okay, sure. What? Let's go back. Let's go back. There's a param type, isn't there? Parameters, params. How do we? All right. Let's do int type. Let's do int. What do we get here if we do this? Named requirements. Parallel quicksort. Oh yeah. Oh yeah, of course other people would be using this when they're messing around with quicksort, right? That's the only time you'd think about this, really. Most people would think about this. Information in the docs. Member types. By the way, CPP-ref is not, yeah, it's not very clear from the documentation, but here it is. Yeah, this is, so come on, man. This is, That's pretty funny. P, the type name, which has a constructor take identical arguments as each of the constructors of D that take arguments corresponding to the distribution parameters. Basically, has a constructor taking identical arguments. Don't you know how to read? How did they figure that out? P, the type name by which some stuff, and has a constructor that, alright, whatever. Alright, fine. Whatever. So it's an identical constructor that feels like that could have been explained a little bit better, but anyway. Yeah, I want to do something like this. Like, you see this? Watch this. Just do like auto of 0 to 100. If I could just do this, that'd be great. It's like, you can't do that. You can't do that. Can I do this? This I think might work. This is kind of funny. This could work. I like that. Please work. Can we? That doesn't work now. Requires initializer. Alright, whatever. So it's const standard uniform distribution params. Param type. P is 0 to 100. No. Interesting. Does this need to have an int? I think it just assumes defaults to int type, but this doesn't default. So you kind of need the whole mouthful to do this. So yeah, you can run that a few times too now. That's interesting. But yeah, so the reason why I'm pointing this out is that you can use one generator for all of the random selections, really for the rest of this whole function. You can do it initially, and then just reset the parameters for each call. But yeah, so there you go. So you can randomly select your pivot. Now, excuse me, we can do something like this, like just auto select pivot. It's going to be this guy. We don't really need to have a routine just for that. Like, that's kind of unnecessary. Let's do, okay, so there's a subroutine which is like sort around pivot. So we select our random number, which we're going to take the D, we're going to say, so int random pivot is D gen, and we're going to use new parameters, of course, A to B, P, and then we're going to say, so yeah, so pick some random pivot, and we're still looking for the index. If we say if random pivot, so we want to first sort everything with regard to that random pivot. So what we would do is we'd put everything that's, we can do it, there's a way to do this, right? So we could put one pointer on the left side, one pointer on the right side, swap the random pivot with the right side, and then everything that's smaller than the pivot goes on the left side, everything that's larger goes on the right side, and we kind of move our pivot, our pointers, and then when you're done, you have the left side everything's smaller, the right side everything's greater than or equal to, and then you're going to swap the right side with your pivot, if that makes sense. So hopefully this makes sense. So A or X, we'll do X and Y, or I and J. I is 0, J is going to be B, and we standard swap the random pivot. We can actually use pointers too into nums, and we can say, actually it would be A. I is going to be nums.begin of A. J is equal to nums.begin of B. And we're going to use auto. And we're going to swap. And random pivot is going to be auto of nums.begin plus this guy, right? And we swap random pivot, what that's pointing to, with what J is pointing to. And now we're going to say while I is less than J, basically, it's going to be, so I less than J means J minus I is greater than 0, pretty much, right? The difference between these two. And this is constant time because these iterators are random access iterators, right? So J minus I is greater than 0, or alternatively I minus J is less than 0. Less than 0, so while I is less than J. We're going to go ahead and we're also going to swap the random pivot with J, and we're going to decrement J, right? And we're going to say if I don't know, we're going to say actually, we're going to do a for loop. And we're going to auto it equals I, copy constructor, right? Plus it. Oh, we want, actually I think this iterator just needs to go to J. Actually, I don't know, how far does this go? Let me think. I actually think it's, I don't know. I'm sorry, I'm thinking about this. I think you do this. Say, okay, say int val equals whatever I is pointing to. If val is less than value, right? So if the value is less than the pivot value, we want to increment I, and you leave it in the same spot, right? It's in the right spot. Else, if value is greater than or equal to the pivot value, then you want to swap I with J and decrement J. But you don't touch I, you leave I. So in any case, I and J are getting closer to each other, right? I is moving further to the right, J is moving further to the left in any of these cases. And each you're gonna process each I and say if this thing is smaller than the pivot value, keep it where it is, and don't move I, or no, and move I. if it's greater than or equal to the pivot value, you want to swap it with j, which is just a placeholder, and then keep I where it is. You're going to check that value, the swapped value next, and you're going to move this placeholder for j closer. And so you could end up keep moving things closer and closer, and eventually I and j are going to collapse onto each other. And now the question is, where is I pointing and where is j pointing at the end of this? That's the tricky thing. We actually want to have, if the last thing was something smaller than the pivot value, then I gets added over, and then I is equal to j at the beginning of j, right at the beginning of the larger things. If j was the last thing, so if it was a larger thing, it would get swapped with j. So this this is larger, it gets swapped with j. J gets decremented, and then it's still a larger thing. It gets swapped with itself, and then j gets decremented. So I is always going to be the beginning of, and j may or may not be. No, actually, no. They won't get swapped themselves. They'll be equal at that point, and they'll actually just stop. And I and j will be, they both, yeah. So in both cases, they'll both be at the greater than or equal to point, and you'll always stop there. So, and they'll be equal to each other. So then you swap back the random pivot portion with now. I guess what I'm not sure about is this dereference point, or is that doesn't give us an integer, that actually gives us like a position. Swap the random pivot with where I is pointing. And now everything to the left of where I is pointing is excuse me, everything to the left of where I is pointing is what do they call that? Everything to the left of where I is pointing is less than, and everything to the right, or including I, and is greater than or equal to. Right. So that should we call that a partition, right? We just partitioned around the pivot. So we can say auto partition to this subroutine. And that would be this routine, right? Basically. So now we can return this I, this pointer, or really just I, yeah. And let's see if we partition, let's partition our nums. Let's run that a few times. I don't know, we have to actually print it, I think, each time, so we can do that. Yeah, all right, let's just do it that way. Let's see what we get. So this is the partition routine that's used in quick select. There's something similar to this. So we'd have, it doesn't say that we didn't print the pivot. We could print the pivot, I guess. Let's actually do that. Oh, nice, it compiles. does that give us? What does that look like? Pivot 1. So that doesn't look like it got pivoted nicely. Can we try again? 1, 4, 6. Okay. So 1. So everything to the left of this 1 should be smaller, and everything to the right should be greater. That doesn't seem correct. Greater than or equal. What happened? What is going on? Excuse me? You gotta be kidding me. You gotta be kidding me. What is going on here? What is going on here? I mean, right. That's not what I was expecting. Alright, so let's look at the swap. First we swap, and we do and then finally at the end, all of our swaps. Let's just do one routine. Oh boy, okay, let's see. 1-5-1-1-6-4. Pivot 1. Okay. So B, so it gets put at the end at B, right over here. And I guess my question is swap where is random pivot pointing to now, right? Because now you swapped what these things are, but do you have to set this random pivot to point to J now? Or do you do that? Oh, okay, that's a little bit better, I think. Pivot is 6. Accepted. What? Wait, what? Wait. Did I just randomly partition it to the correct solution? I'm looking at it like, wait, what? What did we just do? Oh, that's very funny. Well, I think, yeah, everything to the left of this 1 is less than, which is nothing, and then everything to the right is greater than or equal to. So I guess as long as the 1 ends up on the left side, you're fine. Maybe that was all I needed to do. Yeah, okay. Yeah, because what these are pointing to doesn't change, right? Yeah, actually, that's interesting. That makes sense. So this just swaps the contents, and this changes what it's actually pointing to. Interesting. Interesting. Very interesting. Okay, that's probably, yeah, I guess that is what I need to change then. But we can do a whole bunch then too. We can just, let's see what we get. A whole bunch of these. What does it look like? 5. So we move 5 to the right. We do 1, 4, 1, 1, 6. 1. So 5 is here. 1 and swap 5 and 4. That makes sense. So we have 1, 4, 1, 1, 6, 5. And then 1 is less than 5, 4 is less than 5, 1 is less than 5, 1 is less than 5, so that's the first one. 1 is less than 5, 4 is less than 5, 1 is less than 5, 1 is less than 5, 6 is not, 6 is greater than or equal to 5, so we swap 5 with 6, and then the I and the J are at the same spot. And you're actually done there, and the swapping doesn't really change much. yeah, the 5 is already moved, I guess. Yeah, the J is pointing to 6. You would actually, yeah, I think you don't swap this. I think you're actually done at this point. I think you looked at 6, but actually you're done at that point, and then you do a swap here. We can get rid of all these in between steps. Well, let's do 6. 6, well, everything's smaller than 6. Let's do 4. Yeah, 4 is all the way over here. Stays in the same spot. 5 is not less than 4, right? So we do something about 5. So this is the first one. 1 is less than 5. We swap with 6, right? And then 6 we swap with 1, and then I think right, that makes sense. And then we say 1 is fine, so that's fine. Yeah, 1 is fine, and then we get somehow we did this wrong. So this is wrong. This one's incorrect, right? Everything to the left of 4. This 4 should be swapped here. I don't know how what happened here. So let's do pivot equals 4. Just for now, let's do where's 4? Pivot equals 4 is really the end, right? Nums dot begin plus nums dot size minus 1, right? Let's do it this way. Let's see if we always get 4 each time. Yeah, it should be 4 each time. Oh no. What? Oh, it's because of the running it 3 times. Just do it 1 time. Now, why is my program giving me errors or mistakes? What did I do wrong? Excuse me. Okay. This 4 shouldn't get swapped with the 1 here. It should be actually with 6. So I was wrong. I thought I thought that through, but I guess I didn't. I guess I was missing something. So. Okay, we don't want to print the initial swap. Okay, so we have partition and then we print at the end. So the last 2 really should be the same thing. So we really don't need that, do we? Or rather this one we could just get rid of, right? We have that already. Last 2 are the same. It should be after each swap we get something, right? So first we swap 4. Now, yeah, 4 gets swapped with nothing, right? 4 is already in the same spot. And now we print it, right? Now we have J is here at 6. I should be here at 1. And yeah, that's the first swap. Now I increments to 5 here. And there's no swap that occurs. That's this one. Then we look at this 5 and we say this is greater than or equal to 4. So we swap it with 6. I doesn't change, but J comes down. Swap it again with 1, right? So we have 1, 1, 6, 5, right? J comes down again. I doesn't change. I shifts over 1 to 1, 1, 1 for this one, right? So here there's a swap. And J, here it's pointing, before it's pointing at 6 here. That got swapped with 5, it was pointing here. And it got swapped with 6, and it's now actually pointing here. So here's J, here's I. In this point, I moves forward. So no, so this point, yes, from this point we swap with here. Now J is here. And I is still here, but we print after moving 6, we print this one. Now we move I, and I and j are looking at each other, and this got printed. And now we do one more. We check that I is equal to j, and in this case, I is actually before all of the. So I was wrong about this. That depending on whether I or j, if it was the other way around, if it was j that got moved down previously. So I guess they J is always pointing to something that's not a it depends, right? If you swap I mean, I guess you could just figure out which one I or j you should pick. If it's I, or if it's right next to I or behind I or whatever. I guess you can kind of try to figure it out, but I think you should be able to basically get to a state where it's always pointing, like it's to the right of j is always, yeah, so j could be when I and j meet. The thing is, let's say I and j are, don't necessarily know if you don't know what I is pointing to. That's the thing. J is always pointing to sort of and you don't necessarily know what J is pointing to either, because the thing that J was pointing to, in theory, to the right, is always going to be greater than or equal to, right, to the right of J. But J itself could be pointing to something that's greater than or equal to. That's actually, you don't actually know. You don't actually know that. So we can say, yeah, we just do a test and say, if J is greater than or equal to pivot value, then we would swap with J. Otherwise, we swap with J plus 1. And let's see what happens if we do this. Compile error. Okay, that's better. Now we have 1146 or 456. What do we expect? That's what we expect. Now the question is, and what we return. Okay, see, there you go. We could say auto ret is going to be equal to J, and we say if this is greater than pivot value, and we want to say ret. Yeah, we could say we don't change ret, but if it's not, if it's less than, then we actually want to increment ret. And we want to, in all cases, swap random pivot with ret. Same deal. Right, okay. And let's try all these different cases now. Try these different partitions and see what happens. So 4, push it to the right, and then everything should be to the right of 4 and to the right should be greater than or equal to 4. Everything to the left is less than 4. 6 shouldn't really change anything. 6 again shouldn't really change anything. Let's actually run a bunch of different possibilities. We can actually just get rid of this too, I think. Yeah, it's kind of hard to think that through. The what I was just describing here with, you know, what do you swap? Like how do you handle that properly? It's kind of tricky. I don't think it's really supposed to be that hard. It's just, oh, and this is supposed to be random too. I don't think it's that hard. It's just, I don't know. It's like there's probably a way to do it that's a little cleaner, that doesn't have so many issues, so many problems. By the way, this is like pretty well partitioned already by after like it's pretty much sorted after this routine here. Okay, let's see what we get here. Oh, my neck. Oh, yeah, once you sort it around 4, you're pretty much sorted. So look at that. So this pivot, you pick a 1 for one of these pivots. It shouldn't change anything. So that's kind of interesting that this ended up this way. So that's wrong. That's incorrect. That is wrong. Pivot around 5, that's fine. 4, that's fine. 1 again. Now, you see that? Those are wrong, right? Those are wrong. Okay. Come on, man. Gotta go back again. Figure out what's wrong. Okay. Why are we getting these issues, man? So that one's fine. But if we run it again, now it ends up in the wrong spot. Now why is that? Alright, so, oh boy. There's got to be a better way to code this. Like, I've got to look it up, find out, memorize how to do this properly. Man, okay. Okie dokie. So, it says value is less than pivot, increment I. So basically we never increment I. We put J all the way down. Just decrement J over and over again. Swapping I with J. Oh no, excuse me, this value is always greater. All these values are greater than equal to the pivot value. So these all would get swapped with these all get swapped to the right. So you have 1, 1, 6, 4, 5. So you put this 1 with this 5, right? So 1 is here, 5 is here. 5 is larger, so 5 would go over here, right? And then 1 is greater than or equal to. So it ends up over here. No. What? Why is 4 there? What is going on? Why? What happened? Dude, I can't. I don't know what happened. Okay. Let's try again here. All right. Let's see. See what we got here. Okay. 1 and 6. Now you say 6. Swap that with. Whoa. Why? Wait. How come J isn't right here? Shouldn't 6 go here? Not here. It should go here. Why is J not? Huh. Oh, no. What? We don't print the first one, do we? Why not? Why is it so confused? This is after things got moved around, but this is not right. This isn't right. This 6 should be where this 4 is. Or Did the the 1 got swapped with the 4 already? I'm sorry. Okay, that makes sense. Okay, now I got it. Now I'm a little confused. The 1 got swapped with the 4 initially, and then 4 got swapped with 6. All right, so it's like yeah, there probably should be another one of these, so we're not confused. Too confused. Don't really need it, but we'll leave it out. It's fine. We'll just assume this first swap happened. So yeah, 1 and 4 is 1 is here, 4 is there. 6 got swapped with 4. Now 6 should get swapped with this one, which it does. Right, 6 gets swapped here, and now we're pointing here. And here, 5 gets swapped with what? Brother. Okay, I get swapped with 6 gets swapped with 4. Right, J's pointing here. 6. Now J's pointing here. J points here now. Where 1 gets swapped. J now. Okay, yeah. So I is here. J is here. This gets swapped, and now I and J are both pointing at 5. And now they're equal to each other here after this gets printed out. And what you do is you say check I and J if J is greater than or equal to, or J is less than the pivot, you're going to move it, right? J has to be, you need to be greater than or equal to, right? So it's greater than or equal to, we swap 1 and 5, and we're fine. Oh, you know why this pivot works? It's because everything to the right has to be greater than or equal to, that's why. So actually, no, we did it right, we're fine. Everything to the right is greater than or equal to, it's just 1 is equal to 1, that's why it's so confusing. Okay, so we're fine, no, we did it. I think we did what we're supposed to do. So, yeah. Maybe a cleaner way to do this would be, excuse me, you don't need that anymore, and you can do degen, yeah, that should be fine. The reason why it looks weird is because of, everything is greater than or equal to 1, and 3 of these values are a 1, so it just looks funky. But if we use different nums, the partitioning would look fine. I want to, okay, yeah. So let's just relax. Let's call this partition. Let's just, okay. I think it's correct. Let me just see if I can think of a way to handle this better. I mean, I guess we just add this at every time at the end. This return iterator. Because you never know if I and J are pointing to the same thing. You never know if that thing is the end of the smaller values or the end of the beginning of the larger values or the end of the smaller values, right? It's kind of hard to tell with just how this has been set up. It's sort of random, arbitrary. I actually do like this how it was done. I think this is fine. Just this little bit of extra logic to guarantee that we have this right. I think this is good. I like this. All right, anyway, so that's the partition. So the quick select algorithm, what you're going to do is you want to find you're basically going to partition around a pivot, and that pivot should be in the correct spot now. And you're gonna get an iterator to that spot, and you can figure out, you can know basically what the index of that iterator is and compare it to the index you're looking for. And if the index is to the right side, you're gonna split your interval. If the index is to the right of what was returned, you can split your interval based off of you're going to split your interval based off of into a left and a right part based off of the you're going to split your interval into a left and a right part based off of the returned index, right, that you just partitioned around, the pivot index. And if what you're looking for, if the index you're looking for is to the left, you're going to recurse on the left side. you just split on. If the index you're looking for is larger, you're going to recurse on the right side. If it's equal, you're done. Right? You've partitioned and you found the pivot that you're looking for, the index, that value, and that it's already partitioned around that index. So we would say auto it equals partition of AB, right? And then we want to say if really it's like it minus nums.begin compared to it or index. Yeah, I guess int it index. We could just do it that way. We could say if the index that we're looking for is greater than it index, we're going to recurse. Otherwise, if this index is less than this iterator index, we're going to recurse on the other side. Otherwise, and then I guess you just put return this iterator, that position. And you kind of want to just do return, you know, you can do it recursively, that's fine, I think. F of, you know, recurse on one side, recurse on the other side. Otherwise, just return this iterator that you got. And you would say index is greater than this iterator, so we got to on the right side, recurse on the right. So that means we don't change B, we do change A, and A is then becomes this iterator index plus 1, right? Because you don't need to include that. And then you would say on the other side, you would say A doesn't change, but you would do it index minus 1. And curse on the left side. And now we want to say, you could also use a while loop for this, you know, this doesn't really need to be, yeah, you can even do it, you don't need to do this recursively, I'm sorry, it seems kind of silly doing it recursively. Basically while true, pretty much while true. Just say int x equals a, y equals b, x is less than y, and when they're equal, it's return nums.begin plus x, and then you say iterator equals this partition, nums.begin if iterate on the right side, which is, it really should be y. It's going to be x equals hit index plus 1, y doesn't change, and then recurse on the left side, or iterate on the left and the right side. This is iterate on the left side, y equals hit index minus 1, and x doesn't change. Right, left side you move, right side you, yeah. So then, and same thing if index equals it index, return it. Yeah, pretty simple. It's pretty much just an else at the end. I think this should give you the same thing in both cases. I mean, you know, you exit this loop, it should be the same. You don't really need to make it recursive. I think it's not necessary. And now we want partition, quick select. So let's quick select on and then print the numbers. We don't really need that anymore, do we? Oh, you know what? There is something here we need. Oh yeah, no, we have that. The partition does that. Yeah. We want to quick select on the index is going to be n over 2 plus n modulo 2, 0, excuse me, num stat size. N is size. N minus 1. Standard C out. Okay. All right. What does that look like? What do we got here? What have we got? So, interesting. That gives us a quick select. We can get 1 on 1, 4, 5, 6. Right. That. And we want auto it. Let's also print out pivot position. Position, it's going to be it minus nums dot begin, and also pivot value let's see that position 0, 1, 2, 3, and the pivot value is 4. Which is what we want, actually. That's exactly what we're after. Where we want the value where everything to the right, including it, is greater than or equal to it. And if we do an odd number of things, we can do the same thing here, and we can do 11, and we can do 12. Yeah, let's see what happens if we do these two. Okay, so 0, 1, 2, 3, value 4, which is right. 0, 1, 2, 3, value is 8, so everything including it and to the right is larger than it. Now if we put another value in there, 0, 1, 2, 3, 4, we picked a 9, and yes, still everything to the left is less than everything to the right is greater than or equal to. And same thing if we pick. So if you notice, if we're even, it's in the right spot, and if we're odd, it's still in the right spot, right? That's kind of the point of this, is still 4. If we add a couple more numbers, if we add like 13, 14, right? 13, 14, and then a 15 maybe. All right, if we do all these things. All right. So 0, 1, 2, 3, 4, 5. All of these are greater than or equal to 10. And everything to the left is smaller. Same thing here. 0, 1, 2, 3, 4, 5. Right, so these are the medians, basically. We're looking for a very specific value, right? And we're going to partition around it appropriately. So pretty interesting. And you see it's pretty quick. So now, how to get our answer. So that's awesome. That's great. That seems to work properly. Took a really long time, though. It's kind of one of the reasons I was sort of apprehensive to look at this problem is because there's just so much stuff involved. You know, I don't know, something about it. I somehow kind of knew that, like, this is going to be the journey. So we have a partition portion, we have a quick select portion using our partition function. And now we want to implement something else, which is not just a partition of quick select. We now, I mean, once we've quick selected, we've actually already partitioned the array appropriately. We want to create a bijection. And this bijection should be interesting. How's that going to work? Everything on the smaller portion is going to be the smaller numbers. Those are all going to be on the even indices. And everything on the, so we'll say auto even. So we have bijection, right? We'll do bijection. Is going to be, look like this. It's going to say, we're going to int x, we'll say, or index, target index. And we're going to say if target index, or yeah, and then target index, and then we also have another int, which is, well, yeah, we can use this guy. And int index, we'll say, we'll call this int, yeah, sure, we'll do that. Int is going to be median index, we'll call it. And that's going to be it minus nums that begin, right? And we're going to say if the target index is less than the median index, we're going to do some things. Else, we're going to do some other things. Oops. Okay. So basically, we would return two times target index. All of the smaller values, they just basically their indices get doubled. The median indices, the indices that are greater than or equal to the median, those are going to be return. Take the target index, subtract the median index. Excuse me. So these are going to range from k, which is the median index, to n, right, n minus 1. You subtract, multiply it by 2, what you got left over, and add 1. This is going to be on all the odd indices, right? So k maps to 1, and then k plus 1 maps to 3, right? That's the bijection for the indices. Now, this is the interesting part. We're going to loop through, we're going to have int count equals n. We're going to say while count is non-zero, right? Count really just be while count. We start with target equals 0. We say bijection of int new target. New target is going to be bijection of target, right? we're going to swap the target nums of target with nums of new target. And then we're going to update target equals new target, right? So we say, okay, we know where this, we're going to start with the initial position at 0. And we say, okay, we know where this is supposed to be. So we're going to swap it with that value. And, excuse me, we know where this is supposed to be. We're going to swap it with that value there. And then we're going to go to that spot. How does that work? We know where it should be. We're going to swap it with where it should be, which actually the 0 position is in the right spot, believe it or not. So 0 we don't touch. So we start off, we don't touch 0. Don't touch 0. That's always going to be in the right spot. So we go to 1, and we say, oh, by the way, just end. Target has to be less than n. Well, yeah, because there could be one element. There could be one element. Yeah, I'll just handle that case appropriately. So we go to the second element and say, okay, we know where this is supposed to be. We're going to swap it with the value that's over there, right? And the value that's over there is now in this position that we were in. Where should that value go? And then we're going to put that to the next one and swap again and keep swapping with different things over and over. And we actually until I don't know if that makes sense. I don't know if it makes any sense. Let me see something here. I don't know. So we would start with so the first one's in the right spot. This one, we want to swap it with something over here, which is actually 0, 1, 2, 3, 4, 5. The 0, 1 is, it's a small, yeah, this one you multiply by 2. So 0, 1, 2. So it goes with 9 and 8, right? So you get 8 and 9. And then from there, you know where 8's supposed to go. You've swapped the values. That's now in the right spot, but now what your target is pointed to is still not in the correct spot. So now you got to swap it to, yeah, so let's say current position. It's not to target, it's a current position. And we have this new target is going to be previous target, we'll say. Alright, so this is previous target. We're going to swap actually nums of current with new target. And then set previous target equal to this new target. And you're actually just going to keep swapping this current value over and over, right? So then now 8 was 0, 1, 2. You're going to swap 2 with 0, 1, 2, 3, 4. So you swap 8 with 6. Right? And then 6 is 4. Now 10 we said is the larger. So 4 should go to 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. So now we swap 8, which is 15, with 6. And now this was one of the larger ones, so we subtract k, which is 0, 1, 2, 3, 4, 5. Subtract k. And it should be, I think, in the first position. Yeah, or no, 15, subtract k, which is 5, so 0, 1, 2, 3, I think is what you end up with, right? 0, 1, 2, 3. You subtract k, multiply by 2 and add 1, so 3, 4, 5, 6, 7, so 15 goes here, right? So 13 and 15 should be swapped. Okay. Now this 13 is all the way over here, right? It's right before 15, so it's 0, 1, 2, multiplied by 2 and add 1 is 5. 0, 1, 2, 3, 4, 5. So we're going to swap 13 and 10. And now you say, okay, let's do 10 is actually 5, so it would be 0 times 2 plus 1. It's actually in the correct spot. So now that that's in the right spot, I think you actually increment the current value. So I think you can do, you can start at 1. And then we say if current, I think you don't actually need this previous target, by the way. Actually, no, you should. You should. Take it back. So new target, previous projection, you say previous target equals new target, and we're going to say if current equals new target, then we actually can say plus plus current and plus plus previous target. Right? And then we pretty much start over again, where new target then becomes, and then our previous target should be equal to current. Yeah. So then, all right, so we do need to modify this slightly, so that way, and each time, by the way, you just do, it really should be a for loop. Right, every time you move, you decrement the count, and then that you should be done after that. But well, you can just run it to see what happens. But I think wrong answer, nice. But I think here, right? So 10 would be in the correct spot now, because 10 would be, yeah, 10 would end up with 1. So 10's in the right spot. So now we got to look at 9. 9 is in spot 2, and we would say, now here's the question, is 9 in the correct spot or not? So that's the thing, we don't actually know. So this bijection idea I don't think really works that nicely. I don't think it really works that nicely. Yeah, I guess you could do it another way. You could just say that, like, all of the smaller values, you kind of want to just put them in the right spot. So you would say, basically, every other smaller value, you want to swap that with one of the larger values. And you can start from sort of the back. So you can sort of go left to right and right to left over here. And at some point they're going to meet. You could do it that way too. You could try that. So you would do 9 with 15, And it kind of depends if it's odd or even where you start. But so if you have an odd number of things, so these are all the larger values, these are the smaller values, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is an even number. So an even number of things will end with a larger number. Yeah, even number of things will end with a larger number. So we can say the smaller numbers, so the smallest number should be swapped with 9 and 15 first. So 9 and 15, that would give you, so the first swap that you would do, then you do 7 and you skip 1 from here and you go to 12, so 12 and 7. Then this would actually end up no longer on the smaller values. And at that point, you really should be done. Well, this would jump to 10, which is no longer the smaller values, and this would jump to 6, which is also, so if they're equal to each other, as long as sort of A is less than B, you would do this. And then I think at that point, you're probably done because, yeah, this should be a solution, right? Yeah, because this is smaller, this is larger, right? If you had a different set of numbers, like 15, right, instead of 14. Or, yeah. Also, this is kind of interesting, how this got partitioned. Yeah, this doesn't work right, this bijection idea. I thought it might, but I was actually wrong about that. Because you get kind of hung up with, like, it's hard to tell whether or not numbers are in the right spots. I mean, you technically could use, like, you could probably modify that slightly to make it work, but let's just try something different entirely, right? I think something entirely different would be fine. Should be fine. Oh, we actually want to see the partition, not the output. Let's get rid of that and just, we don't need the bijection either. Just so, well, actually, yeah, well, okay. All right, how's that look? Brother. We already did the 15 one. Okay, how about this one? So here, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's odd, which means you're going to end on a smaller value. So you should initialize a smaller value here rather than 1 over. So the odd or even kind of figure out where to start on the right side, and then same thing on the left side. You can figure out which one to start. You always have the same spot for the left side, so you're going to say it's 6 with, we said the smaller ones here. That actually means we actually want to start there. So we do 6 and 13, right? Yeah, the right side is starting on a smaller value, left side is starting on also yes. Yeah, you want to match smaller values, right? That's what you're looking to do. So on the left side now, you increment to 2, you go to 8, and you decrement 2, you go to 12, and it should be 12 and 8. And then now this 8 is going to jump to 9, and this 12 is going to jump to 10, and they cross each other now. and you should be fine, right? Now you know which ones, and one of them is, well, actually just crossing each other is fine. And so you kind of have set this properly. And so this goes increases, increases, decreases, increases, decreases, increases, decreases, increases, decreases, right? That should work. So it depends if it's odd or even where the starting point's going to be, the two starting points. But I believe you can, I don't think you even need the median index anymore after that. You could just quick select and then say left is going to be 1, right, and index 1, right is going to be it's n, it would be, so if n is, you do n minus 1, and then minus another 1, depending on if it's odd or even. If it's odd, it's just n minus 1. Right? If it's, let me think about that. So if it's even, you have to go one more over. If it's odd, then you're in the right spot. Yeah. So we add 1. To left, right, and we say while left less than right. And if n is like 0, then you get negative numbers here. If n is 1, you also get, this doesn't go anywhere. If n is 2, you have 1, 1 doesn't do anything. N is 3, then you would say 2, and it's odd, so you have 2, 1. So 3 you would move, you have the left and the right. And yeah, you would have, the middle element should be, so if it's, if n is 3, you actually should have, you need to have, yeah, you're always going to have more smaller values. And the left is going to be 1, and the right is going to be, should actually be the n, should be just n minus 1, right? Which is interesting. And you swap these two, and then yeah, so that's kind of interesting. Yeah, pretty neat. I think it works. I think it works. Let's see what happens. Hey, there we go. Sweet. All right, let's try these test cases. Oh yeah, we already have that one. What about this one? How about that? What do we get? Wrong. No. Oh no, really? Oh, that's terrible. Oh, you gotta be kidding me. 2, 3, 1, 3, 1, 2. What'd I get? 1, 3, 2, 2. No. Oh no. Oh no. I was afraid of that. Oh, you gotta be kidding me. Oh no. What happened, man? What happened? Oh boy. It's good thing we tested some different test cases. Yeah, you're gonna have more duplicates in the test cases. Oh, I was afraid of this. I was afraid of this. Oh no, man. No, 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 no. So we'll try again. We will try again. What do we get after the quick select? Let's do, yeah, let's do one of these. Okay, what happens here? One, one, two, two, three, three. So, interestingly, what is this index? Yeah, we need to get that index. And then pivot the value. Oh no. What happened, man? 0, 1, 2, 3. Pivot value 2. Uh-oh. Uh-oh. Oh no. I was afraid of that. I was afraid of that. Excuse me. So I was wrong with my analysis saying that the median, there's always got to be this median value that the right number of numbers are greater than or equal to. Wrong. Wrong. Oh no, is this all of this for naught? Did all this just get us nowhere? That would suck. That could be the case. This all could have been for nothing, man. It's all for nothing, man. Well, yeah, you want to do it. Oh, yes, I remember now, right. You actually want to go the larger value. Oh, no, you're fine. It's just, okay, I did it wrong. Yeah, I remember now why. Okay, it's actually fine. Okay, so, let's do, okay, yeah, okay, so, I think I know what to do. I think I have an idea. We could salvage this. We could be okay here. We're going to say the left and the right. This right is actually going to be the median index. And kind of matters what we pick for this. We do want, let me just see. So it's median index. If there's half, so this left starts at 1, median index is here. It doesn't really matter where we start on the right side. Oh, it does matter where we start on the right side. We just want to pick a value large enough. So we would pick 2. I think you start at the median index probably. I think you just start at the median index and then you just say left is less than the median index. And you're gonna increment both left and right. How about that? What happens if we do this? Still wrong, really? What? Oh no, this is what I was saying before about like using the bijection that I was describing. Because you want to put this 1 here now. Oh yeah. Oh no. Oh no, that was what I was saying. But that was the bijection. That was why the bijection was important. You basically want to like interweave these two lists, the smaller values and the larger values. You want to pair them off basically. Okay. How do you do this? How do you do this? Oh no. I don't know. I'm thinking how do we do this? So basically, you want to move all the left values into their correct positions on the right side, and then move all the values on the right side in their correct positions on the left side. But it's hard to do it correct. It's hard to do it. No. Oh no. Oh no. Excuse me. Yeah, the bijection. We need to go back to that. Okay, that was why I had to go use the bijections because. All right. Anyway. Okay. So if target index is less than the median index, turn 2 times the target index. Else, turn target index minus the median index times 2 plus 1. Yeah, if we could map all of our indices accordingly, then we're in good shape. However, how do we do this without using too much extra memory? Right, that's kind of the problem we're facing. This is where we want all of our values to end up at the end of it, but how do we do that? How do you do that? Well, I don't know. You could do like a push and you could like pop everything if you wanted to, I guess. But no, you can't do that. No, that doesn't work. No, never mind. No, don't do that. All right, how do we do this? You could swap the first, the first 2 elements that this one should go here, but this other one needs to go to the next spot here, and then this needs to go to the next spot over here, which then needs to go to that one, which goes to that one, which then goes to this next one, which then this one needs to go to the right spot here, and then that whatever's there needs to go to the right spot there, and that goes there. You have I guess you have a whole cycle of switching things around until things are in the right spots. But the problem with that is that you don't know when you stop where you're going to stop. Yeah. That's why it's not really good. Can't just move this first element to its correct spot. Can you maybe move the back element to its correct spot? Right? So you move this back larger element to the larger of the smaller elements. No, because that's not where it belongs. It actually belongs. It's the larger of the smaller elements belongs over there. It's a spot in the back. And that spot in the back belongs either where it is, or the one that's moved should be actually just slightly moved over. Oh no, man. So hard. So hard. Oh no. Alright, so I don't really know how to do this one then. Or at least I thought I had an idea of how we could do it, but it was just too difficult. So let's just start with this guy, right? So we had a printout of, we had 1 1 2 2 3 3, right? Let's try that. Let's just go with that one. 1 1 2 2 3 3, right? And we want to do 1 and 2, 1 and 2, 1 2. So 2 goes here, 1 goes here, 3 goes here, 2 goes here, 3 goes here. That's what we want eventually. Alright, so now, I gotta keep my voice up, people are probably sleeping now. What we want to do is, let me turn up the mic volume also, so I can whisper, that way people aren't, I'm not waking everybody up. Alright, hopefully that's better. Hopefully you can hear me now. I hope so. Hope it's not too loud. Okay. Sorry about that. Alright, so let me just keep my voice down. It's taking me way, way, way longer than I was expecting it to. It's like 2.5 hours now. So, yeah, we want this, right? This works, right? If we put the 2 here, and this 1 here, and then this 2 here, and then this 3 here, we're in good shape. That's kind of what the algorithm is supposed to do. So 1's in the right spot. This one, so 1's in the right spot. And the second one, we want to swap that with the first 2. So we go 2, 1, right? And now 2's in the right spot. However, that 1 is definitely not in the right spot. So that 1 has got to go to the correct spot now. Excuse me. So now we put, so before we really even stop, we put the 2, we put this 1 where it should have been, which is where this 2 is. We swap this 1 and this 2. And this 2 is one of the smaller elements, and now it's in 0, 1, 2, 3, 4. So it's in the right spot now, too. No, it's not in the right spot now. It was in 0, 1, 2, and now it should be 0, 1, 2, 3, 4. So it's not in the right spot either. So now we put that in the correct spot, which is 2, and this in this spot 3. And now we say, okay, is 3 in the right spot? This 3 is supposed to be in, it's in 0, 1. It should be in 3, 0, 1, 2, 3. So it is in the right spot. And this previous value that you swapped was in the right spot. So now the problem is, even though this is in the correct spot, we don't know. Well, if we have n-1 values in the right spots, we're done. But the thing is, we don't know here if what we just moved into the correct spot, if everything else is in the right spots. Like, we don't, that was what I was saying, yeah, that's what I was saying before, is that we don't know where we're supposed to be moving everything. Yeah. Let me try this again. I think maybe I just had the wrong idea. So let's do for int count equals n. Count is greater than or equal to 1 or greater than 1, right? Because if we have n-1 things are in the right spots, n-n-1 is 1. If it's equal to 1, we're done. And yeah, that's all we really need, I think. Minus count each time. We're going to say auto x, we'll say left is going to start off at the 1 position, and then right is going to be, it's not really right, it's just not even left, but just, current, and then target is going to be the median index, or it. And then we say, okay, standard swap current with it. Swap these two. And then we're going to say int. So we just placed the right value into the target, but now, or rather, no, the target is now in the right spot where it should be. But now what's in the target is that needs to get swapped. So we'll set current equal to it, right? So we put the target into, we put the, oh, excuse me, target. We put the target value where it's supposed to be, but now this value we're looking at, it's in the wrong spot, and we need to figure out where it's supposed to be. And we would say int next target should be bijection of current minus, what do you call that? Just call it auto next, or just int next target current my nums.begin, right? So we get our bijection, we figure out where this is supposed to be, this value. So we have a target value, we have this initial position. Take this initial position. We also want one more thing, I think. Yeah. This is the end. This is going off the side. And something like that. Anyway, so we have the current value, the current pointer, and this median, the target, which is really the median value. And we swap these. Now, swap the values. So this median portion is in the right spot, but this current value, and we set current to that target now. What's at that target's in the wrong spot. And we get the next target from where, really it's where target was pointing. It's where target was pointing. Yeah, that next target's where target was what should be pointing to. No, I'm sorry, it's not the target. It's actually what current was pointing to. It's a little confusing, but now we basically move current to the target, and we have our next target is where we want to go. So we can say target is then nums.begin plus next target. And we do this kind of routine. So I'm not really sure about this. I want to just say like current minus nums.begin is less than nums.size. That's kind of really all we need, just that the index is appropriately bounded, I guess. Just see what happens here. Wrong. Okay. Nice. That wasn't what I was expecting to happen. it should be this 2 swaps with this 1. What do we, wait, what happened? Right, so this 2 swaps with this 1, right? And now 2, 3, 1, 3, 1, 2. Oh no, that worked. Oh no, it didn't. 1, 1, 3, 1, 2, 2, 3. Right, but the 2 is a problem. So this 2 swaps with this 1. We get a 1 here. We say where is 1 supposed to go? Right. So you run your bijection on this current minus nums begin. I'm sorry, it actually is, no, it's, yeah, current is 1, right? And so 1 should go to 0, 1, 2, right? And so we should swap this, we really just should just print it each time, and we'll see it. Brother, this is like taking forever. This was hard for me. This was really hard. Just after the swaps. Okay, what do we get? So 1, 2, 1, 1, 2, 2, 3. Yeah, so we should get this 1, 2, 2, 1, 3, 3. That's what we expect. Then the next swap should, this 1, we know it should be in 0, 1, 2 here. It should swap 1 and 2. Which it does. We get to 1 and 2. So 1, 2, 1, 1, 2, 1, 2, 3, 3. Now we end up with right, so swap this 1 with this 2, right? This is where 1 should be. Now this 2 is in this position, and we know that this 2 should not actually be here. It should be in the original position that it was in was here. But no, it was, yeah, I guess that's the problem, right? My algorithm doesn't really make a lot of sense. Algorithm doesn't really make a lot of sense. One swaps with 2. We know 1 should be in a different spot. We swap this with this 2. And we know this target 0, 1, 2. This should actually be, even though we swap these, this should be 0, 1, 2. Should be shifted to 4, right? 0, 1, 2, 3, 4. So even though this gets shifted to 1 and 2, it should actually end up with 4 or 3. Right? And we should actually be done there. So we get 1, 2, 2, 1, 3, 3. 1, 2, 1, 2, 3, 3. Right? Yeah, 1, 2, 2, 1, 2. Now, this is the problem. 1, 1, 2, 2, 3, 3. Why do we end up here? Why do we end up back to where we were? Yeah, because we did it wrong. Because we did it wrong. We swap this 2 with this 3, and then 3 is actually in the right spot. 3 was here, and that's confusing. This was in the right spot. This actually, yeah, this is, it's 0, 1, 0, 1, 2, 3, 4, 4 minus, it's really 0, 1 here, times 2 plus 1, puts you at 3, 0, 1, 2, 3. It's already in the correct spot, and we would actually just place it in that spot again. And you would be done. You should be done after that. Because you would have 1, 2, 3, 4, 5. Actually, count should start off at -1. Because the first value is always in the right spot to begin with. Still wrong though. This one here. Why does that happen? 1, 1, 2, 3, 3. It should be, you swap the two values, right? 1 with 2. Now you have this 1 is in the wrong spot, but we know where it should be, right? Next target is going to be where this, it's not the target, it's the current that we swapped it with that we want to know where that goes, right? So the 1 gets pushed over there, but the 1 should actually be in 0, 1, 2, 3, really 2. So we do swap that one next. That's the next target. Set current equal to target, equal to this guy. And target is then the next target, which is this guy, right? 0, 1, 2. And then we repeat. So we have current here, target here, and we swap them, right? 1 and 2. It's current here, target here. The bijection is going to be the current value, which is, I don't think that's right. I think it's actually this guy, right? That's confusing as heck. It's where, no, so, oh, that is so confusing. So the initial swap puts the right value to where you are, and then this value ends up in the wrong position. However, the second swap, interestingly enough, we put 1 back to 2, puts a 1 in the right spot, but puts 2 in the wrong spot. Oh, that's so confusing. That is so confusing. I think our target really should be the 1, so we basically need to maintain like the value that you're moving should be the one that's going into the right spot, because we can calculate where it should go, where it should be, right? So really, these should be swapped. We should start with current should be the iterator. It's in the wrong spot, and target should be this guy, right? And now, as long as our target is not out of bounds, we can swap it okay with the target. So now we swap our current with our target, and then now we have a new target, which is whatever where current was. Now that's in the wrong spot, and then we set current to that target, which is now, this thing is in the, that's where we moved it to. No, that's in the wrong spot now. So now, okay, so if we do it this way, we say, okay, we're going to swap 1 with 2. So 1's in the wrong spot, put in the excuse me, 2 is in the wrong spot. We put it in the right spot, and now 1 is here in the wrong spot. And current is set to target, which is this guy here. This 2. What? No. Current doesn't change, right? Current's I'm so confused now. Current wouldn't change. This is not in the right spot now. The target's the thing that's in the wrong spot. Well, they're both in the wrong spot, aren't they? Initially. It's the most confusing thing. Oh no. Oh. Ooh, excuse me. Oh boy. Alright. I don't even know if this is correct, even if I get it to work properly. I don't think this might still just be wrong. It might still just not work. This is crazy, dude. I don't know if I could, like, if I had to code this in an interview, forget it. This just wouldn't happen. This is nope. Let's try again. Let's try this one again. Oh boy. Okay. So forget coding it, right? Because we have to get the idea right. So you swap the median value. You push this first value into the right spot and swap it. Now this 1 is definitely in the wrong spot, and we do know where it should be though. So we can find out where it should be, and then swap it again with whatever that value is, right? So it happens to be 2. And again, we could figure out where 2 should be, and then swap it with where it should be. And then the value that we just swapped it with, we want to figure out what that's supposed to be, and then we swap it. And basically we're done there. That's pretty much it. Now, where this should be, we start with a value that we want to put it to the right spot. So yeah, so we have a current value that's not in the right spot and a target position. We want to put that in the right spot. So what we're going to do is, once we've swapped initially, then in the current value, it's in the wrong position now, right? Still in the wrong position, the current value. We have this target. We can right. So yeah, we can find where this should be by taking this bijection, get this next target, and now the thing is, we have the target is actually going to end up being. Current doesn't change, which is weird. And we have target updates to the next target, right? Right, current doesn't change. And we update our next target for what we're looking at, for where current should be, right? Okay. So that should be here. And we do swap them, and this is still in the wrong spot, right? Current doesn't change again. And we have this new target. And I think this is like a really special case where it happens to work here. This doesn't work. What is going on, man? What? Oh, well, this is the first time. First run. 1, 1, 2, 2, 3, 3. And then, no, dude, what is going on? My brain hurts. This is killing me. This is not easy at all. This is such a, like, can I even do this? I get this feeling like I can't even do this. I'm just wasting my time trying to figure this out. This is too funny. This is basically a, like what do they call that? An in-place merge sort. I should go look that up, how to do that. In-place merge. It's pretty much an in-place merge sort. Sort of, but I can't get it right. I can't get it right. Alright. It's like an in-place merge sort. So, a little bit different. So, let's try again. 1, 2. We swap these two, and we say, alright, this 1 we know is in the wrong spot. This is what this current value was. So, did we get that? We got that, right? 1, 2. No, we didn't. No, we did. 1, 2, 2, 1, 3, 3, right? That's at the top. Now we know that this 1 is in the wrong spot. Okay. Now, what do we end up coding here? We swapped this current value and this target value. Okay, fine. Current value doesn't change, right? Current pointer. We got the bijection of the current position. No, so that's wrong. It's actually the target. It should be the target. Yeah, something like this. Should be. Oh, there we go. It's right now. Now it's correct. Okay. No kidding. Okay. Yeah, and then obviously 3 gets put in the right spot. Now the problem with this though is you'll notice your targets update, but your current position never updates, which might not matter really, actually. I'm just wondering if we have more values, how does this handle larger test cases? I had some larger test cases before, but I got rid of them. I don't know. Start throwing in some larger test cases here. I don't think this works on larger test cases. Just in short, start putting some duplicates in there. Hopefully that's not an invalid test case. No, still works. Seriously, really? What? How does that work? What do you mean that works? What? What? What about this? Does that work? Wrong answer. Okay. It's a little bit better, but I mean, like, I'm trying to get the wrong answer, but how did expected? Okay. All right, let's try this. Got this guy. We got this guy. So this is the input. This is my output, and then what they're expecting. Oops. Okay. By the way, you start to get kind of like hints as to like how they programmed their solution if you kind of just keep plugging in inputs and getting the outputs, because you start to see patterns in what they had out here. But I don't want to cheat. I just want to implement what I thought was right. So yeah, this is what I was saying, that eventually you hit a point where you don't keep iterating. You just kind of stops. If there's like sort of a lot of values, I guess. Even if there aren't that many duplicates. Or actually, hold on. Could say 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Alright. I think actually my output works in that case. It's kind of interesting that it would work there. Yeah, I actually think it's right in this case. Smaller, larger. Oh no, these aren't right. Wait a second. Small, large, but this should be small again. This is too large. It's just wrong. Same thing here, this is just wrong too. Small, large, large again, large, small, large. Yeah, it doesn't really. What does the partition look like on these? After you quick select. Huh. Should get the original also. Whoa. Yeah, I want to separate these. 3 is fine. What does the partition look like on these guys? So this one, the partition is here. Yeah, it looks like 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, looks like 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, so, yeah, I mean, that's fine. This has a median. And it looks like it's 10, 11, 12, this one. Everything to the right of this is greater than equal, and it's like roughly half of the elements. I think we said with odd ones, we want one more on this side, so this would be 10, 11, 12, this would be 11, it actually would be this one. So 14 should be the median point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then there should be 13 over here. No. There's 11 over here. Yeah, 11 over here, 12 over here. Right. That's for odd cases where it would end with this one. Now what's interesting is basically, yeah, we could just take 5 and go to 14, and then go to 6, and then go to 15, and then go to 7, go to 15, and so on, and just interleave all of the values. Now, we don't end up doing that, though. Excuse me. Ends up happening is kind of odd. Yeah. Well, that's our partition. Okay, yeah. So these are the partitions when we're done with them. Of these, this one partitions to this, and the other one partitions to the below. Right. Okay. And the partition's fine, but the algorithm doesn't seem to be correct. So I'm wondering if in these two cases, let me just do this here. Just take these two. Let's see what we get. I think one of these actually is still correct. Let's take the first one out. They really both should work, but somehow it fails. Still wrong. Okay, so they're both wrong. Okay. So yeah, this is kind of what I was saying, is I don't think the algorithm I wrote really works correctly. Like it just, at all. It works correctly for a while, but, oh, okay, I see. No, sorry. Let's see what this gives us. I think the second one is right. That's something I'm wondering. No, it's not right. Okay, neither of these are wrong. Or neither of these are correct. Yeah, they're both wrong. So the reason they're both wrong, I believe, is because while this kind of works okay for a short while, once you're in that position here where 3 is in the right spot, it's not really clear where you should go. Once this median is in the right spot, now you kind of need to do the same algorithm from the other direction, something like that. Like let me print out, let's do like a debug here. I should stop deleting this. I keep writing the same thing over and over again. I'm gonna end up like proving that I can't actually do it the way that I'm trying to do it, and then I'm gonna end up very sad. Okay. And let's print that out. And we'll notice something happening, that there's sort of a point where, you know what I want to do? Actually, I want to print, we only need one test case really for this. And I only want to print when, if next target equals, or if let's do if bijection of target is equal to basically the value's in the right spot already. Whoops. Okay. All right. What happens if we do this? Oh, that never happens. Is that what? Wait a minute, really? 5 and 10. Where does 10 end up here? That shouldn't happen. Okay, well I guess we're doing this then. And I guess we'll just throw that in there too. Okay. Like this never changes, this current, so that's why it's a little confusing. Target position 2, 4, 8, 16, 9, 18, 13, 3, 6, 12, and 12. Yeah, target position equals current position. That's really what we should look for. Let's do the other way around. I don't need that right now. Because once you get here, then you get something interesting. Alright, 5 and 14 is fine, 9 and 15 is fine, 8 and 10 is fine, 7 and 10 is fine, 6 and 15 is fine, 13 and 12 is not fine. Alright, this one, things get interesting. Right? 12 and 12, okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And they're now equal to each other. We have something interesting happen where swap them with themselves. It's in the right spot. But the problem is we don't know what to update our value to, what to increment our value to. I want to say that we should basically just increase the current to the next position and just kind of increment from left to right. Yeah, I guess we do that. I don't know. Let's try this. Counts greater than 0 and targets minus. I really don't need that for current. We could just do target. We could do current actually. Oh yeah, actually this guarantees that the target won't be out of bounds initially because you don't have enough. Right? In other words, if count starts at n-1 and you look for count greater than 1, that means the count's greater than or equal to 2. And that means that n-1 has to be greater than or equal to 2, which means that n is greater than or equal to 3. So you don't have to worry about this. You don't do anything if you have less than three elements. Okay, so we'll swap current and target. Say if current is equal to target, then increment current and target equals the bijection of where current should be, right? Yeah. Not sure if we need this anymore. Let's just see what happens if we do this. And this should continue. don't decrement count here. We just, actually no, we do every time. I'm sorry, that's true. What does this do? Oh, okay. All right, still wrong, but maybe better. I don't know. What happened? Oh, okay. I don't even know. I have no idea. Let's try this. What does this give us? So 2, 4, 8, 16, 9, 18, 13, 3, 6, 12. Okay. Excuse me. So finally, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 7 is in the right spot, basically. It's in the 12th position. I guess 7 initially start off at 6, 0, 1, 2, 3. No, that doesn't seem like it's in the right position. That doesn't seem right at all. I'm very confused. Three, 0, 1, 2, 3 swaps with 12. Or excuse me, yeah, this guy, 15. Okay. Now 7 should be in 6, at 6, I guess. This is after the swap, right? So 0, 1, 2, 3 swaps with 12. Or it's going to swap with 12. Already swapped. There were some things swapped. Now 6 and 12, 7 swapped with 15. So 15's in the right spot, 7's not. And now we have 12 and 12, which is to say that 7 should be at 12. Because it was at 6 before. Or, excuse me, what is that? What? No. No, we swapped 7 back with something. How did that, what's going on? I feel like this is what's about to get swapped, 3 and 12. And then 6 and 12 are about to get swapped. 0, 1, 2, 3, 4, 5, 6. 10 and 7 get swapped. And so 10, yeah, 10's in the right spot here now. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yeah. So this is about to get swapped. So they do. And they're in the right spot. So now you look at 13, which is 15. And 6. Now why is it 6? Why is 13 6? Now that's an important question here. should we move this value now? Because the bijection's only, oh, that's what's wrong, I think. I think I know what's wrong. I see. I see. And target index is less than the median index. And matters a lot. Okay. See the problem. Alright. If you're less than the median index and value is larger than the median value, and the value is less than the median value, no. It's gotta be, if you're on the left side, oh no. Basically, and you're less than the median value, this is the spot you're supposed to be in. Otherwise, you just return you're in the right spot. If you're greater than equal to the median index and your value is greater than or equal to the median value, no, see, yeah, then there's a certain position you're supposed to be in. Otherwise you don't move. I actually don't think that's true. I think it's, no, this doesn't make sense, I'm sorry. It's so confusing. No, it doesn't matter. It doesn't matter. Every value moves somewhere. Every value moves somewhere. The question is whether or not it's already in the right spot, which it could be, potentially already in the right spot. Basically, did we already return to position 13? Yeah, there's these position 16, position 18. I think we end up revisiting these positions. Yeah, we do, which is kind of a problem. Yeah. Oh boy. Oh no. Oh no. So we can do a couple things. Yeah, we can do a few things here. We could say my algorithm, man. Do a couple of things. If your value is greater than, yeah, if it's got to be less than the median value. And the same thing if right. otherwise you don't touch it. But there's another thing here. If you're a smaller value to the right of the median, then it's no bueno. Well, let's see what happens here. If this changes things or not. What do we get here? It's still wrong, but maybe a little bit better. Get to 13 and 12. Oh, that's confusing too. Yeah, there's a value. You have to actually give it the value. That's interesting. The value is going to be current's not in the right spot. I don't know, that's just really confusing. It's still not correct. It's just like really hacked, kind of trying to get this to work. This doesn't make any sense. Nah, forget it. Forget all this. This is nonsense. This is nonsense. There's no way this makes any sense. I gotta just lay down and think about it. What the heck? What do you do? What do you do with this? I don't go rhythm. I don't go rhythm. Just, there's gotta be a way, man. There's gotta be a way. Where do you put all these elements? I want to just move all these elements somewhere, you know? What if you do this? You say, you just put them all where they're supposed to be, right? So swap 9 with 8. Swap, yeah, say, all right, let's do it this way. Let's do it, yeah, so 9 with 8, forget where 8 is, don't even worry about where 8 is. Well, no, but that's the thing, it's like, I guess you gotta go backwards, right? So let's say so it's 12, right? 0, no. This is 10, 11, right? So it's gotta be like here. So if we just say swap 13 with this value over here, which is, I don't know, so this is odd, right? So it's got to be a small number, yeah, so 13 with 15. Then 11 with 15, the next one, 11, 15 with 11, right? just move things backwards every two. 15, 11. So 13, right? 15, 11. Okay. 10 with 15, right? Drop another 2. No, this is wrong. This is wrong. I'm doing it wrong. I see the problem. Right, okay. Let's go back. So this is the initial. It's here, right? I'm doing it wrong. Alright. 13 with 15 over here. Right? 13 with 15. This 12 is going to go in the correct spot as well. Right? That actually goes 12 and 15. Now this probably looks kind of confusing because now we got all these larger values over here, but that's in the right spot, right? These aren't necessarily in the right spot, but this is, right? That's, I guess, the confusing part. Now, right? 13, 12, 15, okay. Now we want to put, okay, all right. We put 12, 13, 12, now 11. Hold on, this is 12, 15, 11. Let me just make sure these are the same. Right, now we say, so I did this wrong, I think. Hold on. Okay. 15 with 13, done. This next one, 12, with this right spot, 12, correct spot. This next 11, should we put in the right spot, 11, 15, swap them, right? This next one, swap with this 15, 10. This goes to 5, 15, right? Next, this 10, right? Jump another 2. This guy here, 0. This 10 goes to 5. So basically we're jumping 1 on the left side and jumping 2 on the right side, right? That's sort of the approach. So we get this 15 and 10 here, right? Now we get 13, 15, 12, 15, 11, 15, 10, 15, 10. And I got this 14. This guy gets swapped with this 10. 14 and 10. Okay. Now, the problem we run into is this is no longer in the larger values here. And what we want to do is put the smaller values in the right spots. We did roughly half of these smaller values. Gives us all of the larger the smaller values and the larger values, but now we have these larger values here, and we don't want to mess around with this part and this part. Before we move these larger values on this right side into the correct spots over here, which, by the way, would be these larger values should actually be in their correct positions. So these were every other larger value from right to left, and their actual positions should be, this one should be here, right, 15 and 15. I think it's better if we do it this with this one. We should actually do it with this one, I think. So it's kind of part of the problem with this algorithm is it's, I don't know, I guess it's kind of hard, maybe, kind of confusing. I don't know. I don't know the correct way to do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 11 means we want, yeah, so it should be 12 on this side. And we do the same thing again. 13 and 23, or 13 goes where it's supposed to be. 12 goes, oops. 12 goes where it's supposed to be. Eleven goes where it's supposed to be. Ten goes, so 13, 12, 11, 10 should be where 20 is. Right. And 18, oops. Alright, so 10 should be where 20 is, we said. And then this 10 goes $18, right? Yeah, 3 10s. And it looks like 14 is the last one we touch. 14 probably goes where the last 10 is. Okay. Now, the question is, the heck do we do from here? Because the problem is now these are all moved in the wrong positions. We roughly know, we know how many there are that we moved, but we want to move these into the right spots now, the correct spots. They need to be pushed into, it's kind of special, right? It's sort of a change of the algorithm, I guess. Different loop. These were over here, and they actually should be put back. So what you would do is you put 23 should be where 24 is. And '24 should be where 17 is. Oops. '24 should be where 17 is. And 23 or 22, yeah, so it should be 23 here. 24 was in the second spot. That should actually be here. The thing that was in the third spot. See, that's the thing, is that these are in every other spot now. These were every other spot, right, from the beginning. And we basically gotta move a bunch of these around. Like, I don't know if it was good to do this. You know, from this state, we're not really sure what to do. Because these are sort of every other number, right? It should be 23, then 24, then 22, then 17, then 16, then 21, then 20, then 19, then 14, then 15, right? Or 15, then 14, rather. Yeah, there's a sort of zigzag pattern. What we should end up with is somehow from here to here. Let's just skip a couple things, and we'll say 23 is here, 24 is here, 23, 24, what's this next one? 22, 23, 24, 22. 17, 16, 17, 16, right? 23, 24, 22, 17, 16. These 5. Right, and these other ones should be end up on the other side, basically. And the tricky thing about that is, how do you accomplish this? How do you get from here to here? And what does it look like after you do that? So, where's 24? 24 is here. 23 is here. So 23 is not here. And I don't know. And 22 is also not here. And 16 is not here. So we have 1, 2, 3 numbers that we moved back to the right side. And 24 got moved up, 23 got moved to the right spot, 17 got moved up, way up, 22 got moved in the right spot, back in the right spot, and it looks like and 15, right? So we have 15, 19, 15, 19, 21, and yeah, 15, 19, and 21. Sort of. We'll just say question mark. Somehow we can go from here to here, where this is now correct on the right side. This is now in the right spots. However, what the heck do we do with this other stuff? Who knows? Yeah, 15, 19, 21. 1, 2, 3, 4, 5. So these 5 end up spread out in the right positions. We take a whole boatload of these, put them in there, scatter those in there. Spread these out, spread those in, and then we have what? We have if we said 14 is the median, right? So everything to the right should be. So basically, I want to say we could do it recursively, where now we have the same sort of deal where everything to the right is larger than the median, and everything to the left is smaller than the median. And I think that can be done. So maybe that's what we do. We say, basically do it recursively, or iteratively, and pretty much everything on the right side for the median, we intersperse the elements appropriately, and then set things up such that the left side still maintains the same property, and then we can we don't need to find the median again, because we kind of should know it, I guess. Kind of should know where it is. excuse me, but depending on how many elements. So if we had 11 elements on the left side, or 12 elements on the left side, 11 elements on the right, right? So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 on the right and 12 on the left. And now we took care of all the elements on the right. So now we can focus on the 12 on the left. And so it's really the first 6 should be less than, and the last 6 should be more than the median, greater than or equal to the median. So basically, yeah, we could just pretty much cut it in half, knowing that if it's even, and we would recurse. We say if it's even, then, or we iterate. If it's even, then we could take n over 2 is the sort of median point. And if it's odd, it's n over 2 plus n mod 2, right? And so we can do this. I'm falling asleep over here. I'm so tired. I need to go to bed. I think I need to just like end the stream here. We'll delete this VOD. Say thank you everybody for watching, and then do delete this VOD. Say thank you everybody for watching, and then come back and explain myself tomorrow with a better algorithm and a what do you call that? And a better algorithm and a what do you call it? An explanation of what we did prior, and then basically cook up the correct algorithm. But from here we can recurse really, but the problem is this question mark in between. How did we go from, or we can iterate again, and reset the median and the bounds and iterate again. But how did we go from this position to this position, right? What did we do? We said, well, basically we're going to put back these 1, 2, 3. These 3 elements. And we know how many there are. We should be able to figure that out, how many we need to put back. And what we did is we interspersed them where 23 swapped with, we said we actually had to shift 24 where it should be, and then 17 where it should be, and then 19, interestingly enough, ends up down here, in this spot. Excuse me. Well, I would say pull these values 15, 19, and 21. No, see, they're interspersed though. It's, yeah, I guess the last 3 values should be kind of pulled out here. 15, 19, and 21. But where does 16 go? Yeah, 15 swaps with 16. 22 swaps with 19. And then 23 swaps with 21. That's not really correct. It's a little more complicated than that. There's kind of a lot of swapping that goes on here and moving around. No, it's not right. Excuse me, because basically these values are sort of every other value, and these had sort of correct positions before they got moved. I want to say it's better to actually move things in the right positions from right to left and from right to left here. So pretty much you take half of this array, these smaller values, this portion, and you swap it around with these values. You mix it into these values, and you end up taking half of these larger values and placing them here. That's pretty much what you end up doing. I don't actually know if it matters very much. Quite frankly, now I'm thinking about it, if it really matters very much. Oh no, excuse me. The reason you want to maintain the order is because the order might matter based off of the pivots. It shouldn't matter, really, actually thinking about it. No, actually, it shouldn't matter at all. As long as these values are greater than or equal to the median, it actually shouldn't matter what the order is. So we actually don't need to maintain the order here properly. We can actually I actually think we can just place all of these, swap all of these with the values on the right side that are greater than or equal to the median, and then it doesn't really matter what the order is. I thought the order mattered. That's, I think, why I'm struggling with this so much, is that I'm thinking the order matters, but it doesn't. If we just place all of these into the right spots and swap them on the right side, we can iterate again over a smaller set and do the same thing over and over again until you're done. Yeah. Interesting. Yeah, never mind. I'm making this way harder than it needs to be. I do kind of want to end here because I want to go to bed, but yeah, now I'm thinking about it, I think this is actually a lot easier than I'm making it out to be. Well, maybe I can code it up. Let me just try it here. So we have 1, 2, 3, 4, 5. We want enough of these elements such that basically we cover everything here until we're past the median point, right? So what does that look like? We do all of that. We get 13 with 23. We get 12 with 22. It actually doesn't matter what I was saying before. We get 16 with 11. We get 10 and 20. We get 18 and 10. And we get 14 and 10. Right? So smaller, larger, smaller, larger, smaller, larger, smaller, larger, smaller, larger, smaller. So this is set. And now we basically iterate again here, but knowing that we have all of these are median values, so we don't even need to count how many we need, really. Yeah, we can just until this is past the median point, which it's 1, 2, 3, 4, 5, 6, and then boom, it's past the median point, and then now we can reset from here. We do want to save where the median point was, because we're going to use that to sort of cut this into pieces. And then we just kind of do the same thing again. Iterate again. Where the new median is. So this is like the previous median. The new median is going to be, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, or hold on, let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6. This becomes the new median. And we do a similar kind of thing again, where we say we start from the back. We go 23 and no, we don't have to start from the back when it's. We do start from the back, but no, we don't have to start from the back when it's when it's even. So 22 can be replaced with 10. Swap with 10. We can swap 20 with 6. We can swap 14 with 7. Right? And then now these become just like so. And this is even again. So we have 6 here. And we would say swap. So it's even, so we can just do 20 with 8. And then this would be over the median, so now we're down to 3 elements. And it would be, so how many iterations we need to go through, but, and so now we have 3 elements. The median is just this value, yeah, 20, greater than or equal to that median, or that's the median we're using, right, what we're looking to use. I realize this median is slightly different than the other medians you might understand. And then so really there's only one element you have to swap with. So you swap 20 with 9. And then now you would iterate again. However, when you're down to 2 elements, you're just done. Base case with 2 elements, you're done. Iterate down until you have 2 elements left. Yeah, and then you're done, and that should be it. And then you have every other element, every even element is going to be something that's less than or equal to that median. Every odd element is something greater than or equal to less than that. Excuse me. Every even element is less than that median, and every odd element is greater than or equal to that median. Now that's kind of a problem, isn't it? Because I think I'm potentially still wrong with this approach. It's kind of what I was saying before, is that if you have a lot of duplicates, you can still run into issues because you could have basically like a large number of the elements are equal to the median, and you'd end up in a spot where even though you can do this, excuse me, you can still end up in a position where the smaller value is actually one of the median is equal to the median, and then the larger value is also equal to the median. Because if you notice on the case before where we were looking at 1 3 3 2 3 1, we ended up with 1 2 2 3 3, where this 2 was considered the median value. That these values are not necessarily smaller. So right, that was why I was thinking that the order matters. Yeah. It's pretty awkward. I don't know, man. This is kind of, it's hard. It's a hard question. Trying to maintain the order. I don't think this is the right answer, what I've got. Like the whole thing, I don't think it's right. Because you can't always get what you want. Because you can't. Yeah, I don't think this whole thing is right, because you can't what was I saying? You cannot You can't rely, the order's not supposed to matter. Excuse me, the order's not supposed to matter. We're assuming that everything to the left is less than the median value. But like I said, there are cases where this median value extends into both the left side and the right side. And so we have a problem. We have a problem. We do have a problem. You can't always get what you want. Try sometime, just might find get what you need. Oh, baby. Yeah, because you could have this too. Could be over here on the left side here. Like you literally, your pivot could have ended up like this after you've fixed everything up. And then even if you keep the order correct, you still have these two sort of colliding into each other, which is not correct, right? It's not right. And so you have problem, you have problem, you have problem. Oh, you can't always get what you want, but if you try sometime, you just might find you get what you need. I think my whole approach is wrong. I think I am just plain wrong. It's wrong. It's all wrong. I can't believe I spent so much time on something that was wrong. It's pretty much where we're at right now. Just what did I do? I don't think this works, man. No, because you're making this assumption that you can split this into two groups like that, but it ain't right. It ain't true. It doesn't work like that. It don't work like that. It don't work like that, sir. Sir, it don't work like that. No, sir. No, sir. Oh boy. It's time for bed. Oh, you can't always get what you want, but if you try sometime, you might find you get what you need. Oh, baby. Wow. Yeah, man. You just as easily could have gotten this, and then this wouldn't have paired off so nicely. Shoot. You can't always get what you want, but if you try sometime, you just might find you get what you need. Oh, baby. Excuse me. That's crazy, is like, if you just sort the left side and the right side, then you can do, just pair off as described. This one with this one with the next one, this one with the next one. Like, there's so many ways to do this that's so much easier to understand and to do very quick, that doesn't use like n log n time and linear extra space. It'd be like super easy. But with those bounds, it becomes like just way harder. I don't know, man. I think Excuse me, you get kind of messed up. You get kind of messed up with this test case. Even if you did all of this correct, it'd still be wrong. You gotta somehow pair this off with something here, and this with the other stuff, other things. The values that are equal to the median, you gotta pair them off with something larger. I mean, I guess you could do that first, you know. First. You can't always get what you want, but if you try sometimes, you might find and get what you need. Oh, baby. I would say that's probably all you need to do. You can probably still use the same algorithm. It's just you need to check from left to right of all the things that are equal to the median. You need to pair them off with things on the right side that are larger than the median, and just kind of like put them off to the side, and yeah, you could do a little bit of extra processing. Just kind of, you could actually run. You could run this whole algorithm basically twice. So the first time you partition and you scan on your left side for all the numbers on the smaller side, all the numbers that are equal to the median, and then look to basically pair all of those off, you know, sort of left to right with values that are larger right on the right side. Kind of just scan through and pair them off. And then what you're going to do is it doesn't matter the order or anything. Then you're going to actually shift your range of values to the smaller array, the array where you know with certainty now what's left over are things that are strictly, you know, now you have a group that's greater than or equal to the median and a group that's smaller than the median after that point. And then you can basically partition what's left again, and it should be, yeah, you should be basically you basically run the whole algorithm again, sort of, but this time with a new median, and I think this time you can guarantee that the median, it should be the same value again, and because you didn't do anything with that median value, you removed just as many elements that were less than it as were greater than it, or less than or equal to as were greater, so it really should end up being the same value again. And then now you have this, now you can understand that everything to the right, you know, partition again, get a new median, get the same median, should be partition again, and now you can iterate on that set using the algorithm that I've described, where it's guaranteed now that this median is greater than or equal to, and everything to the right is greater than or equal, and that the things on the left are smaller. And then you can go through this whole routine here that I was describing. This works fine after that, after you basically just, you know, paired off the values that are kind of problematic on the left side. Yeah, that's pretty much it. That's pretty much it. Yeah. Yeah, you kind of want to move. Yeah, as you find these values on the left side, you kind of want to swap them into like sort of every odd slot, I guess. And then on the right side, you're going to just loop down to find values that are greater, and then just kind of put them in the right slots. And then once you're done with that routine, then you can sort of reset your bounds and then partition again, and then do this algorithm that I was describing here, where things are roughly in the right. Actually, you don't need to maintain the order anymore for this one, so you can do the left to right algorithm that I had here before, where you basically just just replace the small ones with the large ones left to right until they're in the right spots. That's pretty neat. So actually, this is pretty easy. If you just break it up into two pieces, partition once, get rid of all the hairy, tricky stuff, and then partition again, and then move things in the right spots. Actually, this is like a very easy algorithm. Very easy solution. I don't know why I'm struggling so hard with so much on this. I spent so many hours. I don't know how many hours. 4 hours. Almost 4.5 hours now. We'll come back to this tomorrow, I think. But yeah, this took me forever to get the partition right, and then it took a while to get the quick select correct, and then then I realized you actually want to use two quick select routines, two quick select calls, and then two kind of readjustment calls, and then you should be able to do this in expected linear time and constant extra space. Excuse me. You technically can your quick select you can guarantee linear time with quick select, but what you would need to do is use an extra logarithmic space to get the guarantee in the worst case. So it can be done in linear time, expected linear time, but not on average linear time, but not it's almost certain going to be linear, but there are worst case scenarios that could happen in theory. They're very unlikely, but they could happen, that are quadratic. So for the quick select, but they pretty much won't happen because your random generator is randomizes the selections of the input. So even really bad input, it could still be fine. But you could have really bad input and then run your algorithm enough on it to actually get a bad runtime, but it's very unlikely. So yeah, that's the approach I'm going to take. Obviously, I got destroyed by this problem. Really had to think about this a lot. I think I have the answer now, but yeah, as you can tell, I was pretty apprehensive to try to get into this problem or work on it, because it just seemed so I don't even know if they could do this kind of a thing. I got wrecked, man. I don't know. This is a problem that I think someone asked me to solve this problem a while back. Somebody asked me to take a look at it on stream. This was a long time ago, and yeah, man, I got destroyed. I don't know. I didn't look at it because I was like, oh yeah, eventually I'll look at it later. But they were like, no, look at this problem. And I just could see why they wanted me to look at it, because this problem is hard. Or at least it was hard for me. This problem was hard for me. I should read the discussion too to see what people did. You know what I'm gonna do? I was going to delete this VOD because of just hours of me pondering. But I actually kind of want to keep context and keep this video so people can see how much time and effort and thought I put into trying to figure this out, and then so I have it for reference too, and then I'll just put make a part 2 that's a lot shorter, that basically has the answers. We'll go through it all again, but make this a part 1 where I didn't actually solve it. But yeah, so thank you all for watching. I will talk to you all soon. And yeah, this was a tough problem. This was a hard problem. I really struggled with this one. Just give me one moment here. I'm gonna end the stream, and then I'm gonna change the title. I'm gonna end the stream and then change the title and the replay. So, all right. Thank you all for watching. Take care. Have a good night.